Welcome to my Pygame platformer tutorial where I will be covering the basics of Pygame and quickly ramping up into creating a full platformer game where you're a ninja who can run, dash, jump, and wall jump around while fighting enemies and beating levels. If you don't know who I am the Fluffy Potato. I've been working with Pygame for over a decade. I've released 2 Steam games with it, won multiple game jams, and just won the graphics category of the last Ludum Dare with Pygame. This tutorial is for anyone who has a decent understanding of Python. I expect you to understand the basics including lists, dictionaries, and a bit of object-oriented programming. If you're not comfortable with object-oriented programming, you can check out my old Pygame tutorial series where I did the whole thing without it. Whether you're brand new to Pygame or you just know the basics and you want to learn more, this tutorial is for you. We'll start with the basics and work our way up to some advanced topics like level editing, visual effects systems, AI, and more. As you follow this tutorial, there will be several breakpoints for which I've uploaded the project files to a resource page for. There will be a link to this page on screen and in the description. This means that if you make a mistake, you'll have a working reference to figure out what went wrong with. Additionally, all of the resources, code, art, sounds, music, etc. for this tutorial are released under the public domain. You can use them for whatever you want and even make something you'll sell with them. Before we get into Pygame, I'd like to give you some tips on getting the most out of this tutorial. The overwhelming majority of people will learn significantly better through experience and experimentation than by just listening. It's important to be coding along with me in some sense during the tutorial. It doesn't have to be the exact same thing, but making something will help you both understand the topics and remember them. It would be a shame if you sat through 7 hours of a tutorial and then forgot all of it the next day. Also, it's important to not just copy what I'm doing. If you're following along, it's important to periodically pause the video and try changing the code I write to do various things to ensure you understand what I'm doing and how it might be used for other purposes. Tutorials are most valuable of a learning experience when you learn to apply them to a broader use case than the specific topic being covered. Now let's get a bit into Pygame. So what is Pygame? Well, in technical terms, it's the Python wrapper for SDL. SDL is a media library widely used with C++ and C to make games and other applications. In other words, Pygame is the adaptation of SDL to Python. If you're curious for more details, I have a video dedicated to the more technical overview of how Pygame works and its implications titled Pygame's Performance: What You Need to Know. The important thing to understand is that Pygame is actually considered a pretty low-level way to make games. There is no such thing as an animation, a camera, or even a player. We have to code all these things ourselves, and I'll be showing you how in this tutorial. Pygame gives us user input, and we have to create a window and generate every frame of the game primarily by just telling it where to put specific images on the screen. This approach has upsides and downsides. It's an incredible learning experience that teaches you things that are very useful in the software engineering field. In my case, I've found that lots of my experience with Pygame translated very well into being able to work on rockets and flight simulators as a software engineer. Additionally, working at this level gives you a high degree of control over how things work, and once you've developed the basics, you can reuse things you've already made to enable you to develop games rather quickly. My performance in game jams can attest to the fact that you can compete with people using game engines when you're using Pygame. The downside is that the initial learning curve is steep, and the initial progress can be slower than using a game engine. So if all of that sounds good to you, it's time to get started by installing Pygame. To install Pygame, you need to use Python's package manager, pip, to install just the package Pygame. Funny enough, there's a recent fork in Pygame because of some open source drama stuff. I have another video about that if you want to look into it. So there's actually 2 versions. There's the original one, which is just Pygame, and then there's another one, which is Pygame CE. I've been using CE lately, and at the moment, I think that's the better option. I'll keep the pinned comment updated with what I recommended. For this tutorial series though, I will be using CE. At the moment, there's not too much of a difference between them. All of the stuff that I'm covering in this tutorial will work in both versions of Pygame. So to install it, like I said, you need to use pip. The way that you would normally do it is just type pip install and then Pygame or Pygame CE. Although the problem is that sometimes it's pip, sometimes it's pip3, sometimes you don't have that bound at all, and you have to do Python pip but then sometimes your Python is not under Python and it could be under Python 3, and funny enough, in my case, it's just under Py. But actually, if you're doing the Python thing in the front, you have to do a -m. That's the Python module, and you're then calling the pip module and telling it to install Pygame. So, like I said, it would be Python 3. If you're on Linux, normally it's going to be Python 3, I think. I would assume it might be the same on Macs, but for Windows, it's all over the place. So just try them all. Something to check is to make sure that you're not using Python 2. So if you just type Python, you can see your version, and you don't want this to be a 2. It needs to be a 3. So in my case, I'm using Py, so I'm going to do py-m pip install pygame CE. Alright, so it just installed. With that, I can just run the shell by just typing py, and then I can do import pygame, and then you can see it imported. If you get an error on that import, then it's not installed correctly. It's also possible to get an error when you're installing it. Typically, you're just going to have to Google it. If you get an error while you install it, all sorts of things could have happened. Usually it's because you did something weird with your setup, but for most people, it should install fine. And then if you get the error on the import, it just means it didn't install correctly. If Python, and Python 3, I don't actually have this one. If none of these start the shell for you, you're going to have to find your Python install so that you can actually use that. There's a million things that can go wrong in this part because there's a ton of different ways you could have Python installed. So I can't go too into depth here. A lot of this stuff is kind of just general installing packages with Python type stuff. So if you run into issues, you can just Google it. Anyways, with Pygame installed, it's time to go ahead and create our very first window. All right, so I'm just in a folder that just has the assets in it for the project. I'll get into those later, and there'll be a link to those assets in the description so that you can follow along. But for this first step in making the window, you don't need those to begin with. So let's go ahead here and just create a new file, and then we'll call it game.py. So the very first thing you're going to have to do is just import Pygame. And then after that, the next step is to do a pygame.init. This will start up Pygame. After we initialize Pygame, we can create the screen or the window or whatever you want to call it really. So we can just name our variable screen, we can call it window. I like to use screen. I don't know where I got this from. I think I found it in some example code like 10 years ago, and I just kept using it ever since. But we'll set that to pygame.display, and then we'll do .setMode. So this is a bit of a misleading function. This is actually the function that creates the window, kind of. For some reason, it's called setMode. There are technical reasons for that, but it's a little bit confusing. The next argument is going to be the resolution, and we pass that as a tuple. So I'll say 640 by 480. That's the resolution of our window in pixels. So just this function call here will create our window, and then this is kind of the handle for a window so that we can draw onto it. The next thing we'll need is a clock. The use of this is for forcing the game to run at 60 FPS, because normally if you run code, it'll just run as fast as possible. But in games, you might want to restrict that because you're running a lot of stuff in a loop. Every frame is its own iteration in the game loop. So if you ran it as fast as possible, you would like max out your CPU and just your fans would go brr and stuff like that. So that's not ideal. So a lot of times you don't want to run it at the maximum frame rate. Another thing worth noting is that normally you would use something called delta time, which is the difference between the time in the frames, in order to just kind of change how fast things are moving and stuff like that to adjust for frame rate. We're not going to get into that in this tutorial. I'm going to work with a fixed frame rate because it's a lot easier mathematically. So that's another reason to try to set up something so that we can restrict the frame rate to 60 FPS. So for the clock, as you can see tab 9 suggesting here, it's just pygame.time.clock. So that will instantiate a clock object, and then we can use that for a couple of things. The next step is to create the game loop. So the idea is that, as I mentioned, in a game, each frame is an iteration in a loop. And in that loop, Some games will have multiple loops running at the same time, like maybe one for rendering and one for physics and stuff like that. But in our case, we're going to do it all in one loop, and every loop you'll have to update everything, and then you'll have to put it onto the screen, and then you'll finally update the screen at the end so that the user can see it, and then you go to the next frame. So the idea is that games run in a continuous loop, and you're just constantly working with changing data, and the main thing that affects that data is the input that the player gives, which you also pick up in that loop. So to do this, we'll just do a while true, so that's an infinite loop. And then in here, we can do a pygame.display.update. This will update the display. So we can draw onto the screen, but until we actually call this function to update the display, we won't see anything changing. By default, the screen's just going to be black. So if I don't call this function, you're just going to get a black screen. And after this, we'll want to do clock.tick 60, and that's for 60 FPS. So this will force this loop to run at 60 FPS. So this function in itself is effectively just a dynamic sleep. It'll sleep for however long it needs to maintain that 60 FPS. There's other stuff the clock can do, but we won't need any of that for this tutorial. Alright, so the next step is to get the input. If you were to run the code right now, a window would pop up and it would work, but we don't want that because in SDL, you have full control over the input handling. If you don't ask for the input, Windows will think you're not taking input. And if Windows thinks you're not taking input as an application, it doesn't matter if you're updating the screen. It will think that the application has stopped responding, and it'll do that thing where it grays out and gives you the spinny thing on your cursor, and it'll ask the user if you wanted to shut it down. So to prevent that, we have to get all of our events and then process them in some sort of way. So we can do a for event in pygame.event.get. So pygame.event.get is what gets the input, and this is where it kind of interacts with Windows and gets that user input so that the thing doesn't freeze. And then in here, we can do something with our input. It can be whatever we want. An event is just like, it could be a button press, it could be someone clicking the mouse, it could be someone even moving the mouse. I think there's some touch type events and other weird things that can happen. There's events for like resizing the window. There's all sorts of stuff. So the way this is structured is that the event will have a type attribute that specifies what type of event it is. So we can do if event.type, and it's suggesting it here is pygame.quit. So the pygame.quit type just means that you click the X on the window. So believe it or not, we actually have to code the part where you click X on the window and it closes. So to do that, we do a pygame.quit, and we can do a sys.exit. Sys.exit will just kind of exit the application. For that, we need to import sys up here. Pygame.quit will just close Pygame. So you need both of them. Anyways, we should have our window now. Here we go. This is our window. We can drag it around, and I can click X, and it will close. And that's all that is so far. One more thing that we might want to do, if you notice, the window name is Pygame window. We might not want that. So let's go ahead and change the window caption. We can do pygame.display.setCaption, and we'll say Ninja Game, and that's the name of our game, I guess. And if I run it again, it now says Ninja Game. You can also change this icon here in the top left, but I won't really get into that in this tutorial because it's not super important. Anyways, it's time to give you a bit of a tour of some of the assets that I have prepared for this tutorial. I will link them in the description. It'll just be a zip file you can download. Just make sure you have it set up the way I do, where it's just a folder, and then you drop the data folder inside that other folder, and then the game script is right next to the assets folder. So inside of data, we have a few things. So we have this music file. We have sound effects for a few different types of sounds. We have maps. I'll show you how you can make your own, and then I'll also do the level editor and everything. But I do have these pre-made because they can take a little bit of time to make. If you look in these at the moment, it's JSON if you're not familiar with that format. And it's just a mess of data. You can try to read it if you want. It's not a good idea to try to edit this by hand. That would not be a fun time. That's what level editors are for. Anyways, if we go into images, this is where most of the stuff is. We have things like a background, a gun, a projectile, and then we have other stuff. We have a tiles folder with a bunch of random stuff in it. Like, I think this is a tree. No, that's a crate. Okay, that's flowers. The tree is, I think, this one. Yeah, here's the tree. We also have our tiles right here. So this is like the different grass tiles. I'll show you how to auto tile these as well, so that you can just place some tiles and they'll form with their edges automatically and everything. And here we also have like different types of particles, just a bunch of images. And then we have our different entities. We have a player with a bunch of different animations and like the enemy, and there's a bunch of frames for that animation. And like I said, we'll get into animations later. And then finally there's the clouds. But we'll get into most of that stuff later. For the time being, the main focus is going to be to show you the basics of using Pygame so that we can get started with the project. In order to make a game that's easy to work with in terms of scope, a lot of times it's good to use object-oriented programming so that you can like pass objects around and just get a lot of the other conveniences of object-oriented programming. I probably won't lean all the way into object-oriented programming for this tutorial, but I will use a lot of that functionality. So the very first thing you're going to want to do, which is a common thing, is to make your game its own object. So let's do class game, def init, self, and then in here we might want to do a few different things. So we can take all of this stuff and indent it so that it goes under init, and then we can do self.screen, so that's an attribute of our object. And then the other part of this is going to be the run function. So this is how the game runs. So you can initialize it and run it separately if you want. So we indent that in, and it loops now in its own function. And the only thing is we have to do a self.clock.tick. And then finally, we have to actually initialize our game and run it. So down here we can do game and then .run. So since this will return the object, the .run will just be called on the initialized object. So if we run it, it should be the same. We get the window and everything. And this is an easier form to work with games in. Alright, so let's get started with actually putting an image on the screen. To do that, we use Pygame's pygame.image.load function. So we can do, let's say, self.image equals pygame.image.load. And then you just give it the path as a string for the argument, and then it'll be able to load it. It can do PNG files, JPEGs, and a couple other types, but usually you want to use PNG because it's lossless. So let's do data, images, clouds, cloud1.png. So we're loading one of the cloud images. So with this image loaded, nothing's changed yet. We actually have to put it on the screen. To do that, we use something called the blit function. Do a screen.blit, and we can do self.image, and we can put it wherever. Let's say 100, 100. Actually, this has to be self, but actually let's do 100, 200 so you can see the differences in the dimensions. Alright, so if we run this, you now see a cloud here. If you notice, I put it at 100x and 200y. So the way the coordinate system works is that the top left is 0, 0. This is actually quite different from how you normally have it in math. In math, it would be either the center is 0, 0, or it would be like the bottom left is 0, 0 if you don't want to have negative numbers. And actually, if you get into computer graphics where you're writing shaders, it would be that way. But for Pygame and other non-GPU based rendering techniques, the top left is often 0, 0. And that's, I believe, has something to do with how when we read text, we start in the top left and just kind of in the order of elements. So say you were to make a website and just place a bunch of HTML elements, it would go from the top left. So yeah, we have 100 pixels from the left side of the screen and 200 down from the top. So yeah, as you can see, we have our nice little cloud there. Now that we have our cloud, it would be nice if we could move our cloud. To do that, I'm going to add a couple variables here. So let's say self.image position equals 160, 260, and then we can use that position as the input over here for our blit function. And something interesting about blit is that the idea is that it's just kind of a memory copy. You're copying some section of memory onto another surface. And blit is just the terminology used for that. And you'll notice that I said surface there. So in Pygame, a surface is basically just an image. So the window itself has a surface, which is the main one you render onto. That's the screen. That's a special type of surface. But most surfaces are kind of like this image one, where it's just an image in memory. Doesn't necessarily represent the screen or something like that. So if you wanted, you could do it the other way around, and you could actually blit the screen onto the image because they're both surfaces, but we don't have a reason to do that. You can blit any surface onto another surface and then at a given location, so you're just merging together different images. If you were to actually blit the screen onto our cloud image, it would erase the cloud and replace it with all black because, well, the screen is black by default. One interesting way I've heard to think of this is that you're just kind of making a collage of different images that you're putting onto the screen, and you can put images onto your images and do whatever you want. Alright, so with this image position attribute implemented, let's go ahead and get the movement part working. So let's add a movement variable, self.movement equals false false, and let's say we want to move our cloud up and down. So we go back to our event loop here. Remember, we get all the events with event.get, and our event has a type. So the type for a button press is if event.type is pygame.keyDown. That means that you pressed some kind of key down. To find out what type of key was pressed for that event, we can do if event.key is pygame. And we'll use k up. So that is the up key. And we'll set self.movement 0 equals true if you press the up key. If event.key is pygame.k down, self.movement 1 equals true. So something interesting to note is that these events are fired when you press or release the keys. They don't necessarily mean that you're like holding it down in that moment. So you're not going to be getting this event every single frame while you're holding it down. So we have to have something to keep track of whether or not it's being held on our end. There are functions that Pygame has for checking if something's being held, but I like to use my own systems for this because it's easier to hook on some extra stuff if you want to change something in the future. Alright, so aside from the key down event, there's also the key up event, which is the same thing except the key was lifted up instead of being pressed down. So we want to switch our movement variables to false. So the way we're doing this is that we have these two booleans here that we're updating based on whether or not the key is held down. So if the first one is true, that means we're holding down the up key. And if the second one is true, that means we're holding down the down key. So with that, we can use that to modify our position here. So we can do self.imagePosition 1 plus equals self.movement 0. Actually, we should do self.movement 1 minus self.movement 0. I'm using an interesting trick here. So booleans technically can be converted to integers implicitly, and that's what I'm doing here. So a true will get converted to a 1, and a false will get converted to a 0. So if we hold down both, we get this adds up to 0. If we hold down just down, it'll add up to 1 because of this one. If we hold down just up, it'll add up to -1. If we do neither, it adds up to 0. So we're able to just kind of calculate how much the position should be changed based on these two booleans. If we wanted, we can change the speed by doing this and like adding a 5, which actually I'll leave that for now. If I run this and I press up and down, we can see the cloud is moving, but we have a weird effect. It seems to be leaving a trail of some kind. And the issue here is that, if you recall correctly, the screen is just, as I mentioned, a surface. So we're putting the cloud onto the screen, but we're doing that every frame at a different location if the cloud moves. So we're rendering the cloud on top of the previous render, which already had the cloud rendered. And you do that a bunch of times and you end up with a trail. What you actually have to do is you have to clear the screen after each frame. Usually you'll be generating a whole image from blank screen essentially, and you do have to clear it yourself. So to clear it, I'm going to do a screen.fill, and we want a nice sky color. So we'll do 14, 219, 248. So .fill will take a color in RGB, so this is the red value, this is the green value, and this is the blue value. So it's a very blue and green color. It'll fill the screen with that color. So anything that was there previously from the last frame will be just completely replaced by a solid color that we just gave it. So if we run this, we now see that we have a cloud. If we move it up and down, we don't get a trail anymore. But now you see there's this black box around it. If you look into our assets and you go to the clouds here, and you open up this image, you can see that it actually does have that black background to it. There's no transparency automatically in it. So what you normally do is you add a color key. There are ways to just use the transparency built into the image, but it's easier usually to have like a background color that you just replace. So in our case, we're going to want to add our color key here. We'll do self.image.set color key, and then we'll say 000. So 000 is the color for pure black. And if you notice before in the image I showed you, the background was pure black. So we set the color to 000, and that color will be replaced with transparency whenever that image is rendered, or rather that surface is rendered. So the color key allows you to just say that one specific color should be transparent. And now if I run this, you can see there's no black background to our cloud image, and I can move it up and down just as you'd expect. Alright, before I get into the next part, which is going to be collisions, there's something else I want to share to you about input. So for this tutorial, I will be using a slightly unpopular, but what I find to be kind of accessible keyboard layout, where we use the arrow keys for movement, and then we use X, and then if we needed another one, C, but we won't for this tutorial, for extra like abilities and stuff. So the idea is that many keyboard layouts will be quite different. So specifically, if you look at WASD, if you go to a different keyboard layout, they're not going to be next to each other anymore. So using the arrow keys for movement is actually quite universal. For example, it works in QWERTY, which is what I'm using. It works in Quartz, and it works in Azerty layouts. So lots of, I think mainly Europeans, are able to play games that use layouts where you have the arrow keys. And the other thing is that for the abilities, like I mentioned, you use X and C a lot. The reason for that is because those two buttons are actually next to each other in all three of those formats I just listed. I think the major format where they're not going to be next to each other is Dvorak, but I don't think there's much you can do about it at that point. There's a reason why a lot of people use X and C. I definitely get a lot of complaints for not having WASD in my games. If you want, you can add it yourself. For example, these keys become like just KW if you want to use that. In the Pygame documentation, there's a whole list of all the keys so that you can just bind it to whatever you want. And one thing you can do is you can actually just support both, so you can have it working with WASD or the arrow keys simultaneously. And that's a common solution as well. So with that out of the way, let's get into collisions. So when I say collisions, I'm talking about collision detection. I'm not talking about there's a wall, you run into it and it stops you. I'm talking about there's an area, you run into it and you know you've collided with that area. So that type of collision detection is the very first step of getting physics implemented. And it's quite simple to do in Pygame. And this is one of the few, I guess, physics-related things that Pygame actually supports, which is just basic rectangle collisions. So here's what we're going to do. We're going to have just kind of a basic area that we can collide with. We'll just call it self.collision area equals pygame.rect. And then we can do, let's say, 50, 50, and let's make it like 300 wide and 50 tall. And then we'll also want a rectangle for our cloud image. So let's do image r equals pygame.rect. And then we can do image position 0, image position 1, and we do image.getWidth, image.getHeight. And this is actually going to be a self on all of these because this is an attribute. Alright, so there's actually a shortcut here, which I won't be using in the rest of the tutorial, but I use it when I'm writing code myself, which is use the splat operator. You can actually do pygame.rect and just splat self.image position and then self.image.getSize, and that will just spread out the arguments, but I won't be using that here because it's something you have to learn that a lot of people don't actually know about Python. If you do know about it, feel free to use it. It's very convenient, but if not, that's also fine. Alright, so the pygame.rect function creates a rectangle, which kind of just makes sense based on the name, and that rectangle has a top left position, which is defined by the first two parameters, and then the second two are the width and the height of the rectangle. And remember, the coordinate system is from the top left, and it's just right is positive x, down is positive y. So There's a couple of different things you can do with these rectangles. The basic functions are things like drawing that rectangle onto the screen. You can draw it as like a box, or you can draw it as a filled in rectangle. You can also do the collision detection with them. We'll be doing both here. So right now we have this one rectangle which we don't want to move, that we're just using to test our collisions, and we have our image rectangle, which is created every single frame based on the position of our image. So the position is coming from that position thing right here, and then the size of the rectangle is being pulled from the size of the image, which you can get with get width and get height. So that will create a rectangle that perfectly matches the image that we're rendering here. Alright, so now we can do our collision test. We can do if image r.collideRect self.collision area. That means that in this frame, our two rects are overlapping in some way. And what I'll do for that is I'll draw the rectangle, draw.rect, and we'll draw it onto the screen, and let's give it a blue color. A bright-ish blue color, but not the same one as our background. Alright, and then we have to pass in the rect that we want to draw. So we want to draw our collision area rect with the color that's like mostly blue and onto the screen. Those are the three arguments of Pygame to draw.rect. And I'm going to copy this. I'm going to say else, and then this is if we're not colliding, we use a different color, which is going to be darker. Alright, so if we run the game, you see we have that rectangle up top. We can move our cloud up and down, and if our cloud touches it, it turns to a brighter blue. So you can tell if our cloud is touching that box with that code we just wrote. And this is, as I mentioned, what we'll use to do our tile physics and all sorts of other collisions later. Alright, so something interesting you may notice here is that the cloud is showing up behind our rectangle. This is probably not ideal for what we're doing here. You would expect to see probably that the cloud is on top of the area we're colliding with, just from a visual standpoint. So the way that layering works in Pygame is that it's purely based on the render order. Remember, you're just kind of copying an image onto another image. So if you happen to copy one image onto another image before you do a different image onto that same location, that second one will cover the first one. So layering is done entirely based on the order that you render stuff onto the surface. If we want the cloud to appear on top of our collision area, we just have to take this code and paste it under the rendering for the collision area. That way this is rendered on top. Alright, if we run it again, we can move our cloud up and we can see it's actually on top. So this can create some problems if you have a specific order you want to like update things and render them in. So you might have to do a little bit of problem solving to figure out how you want to implement your rendering orders into your update sequence and stuff like that. It's very common to separate your updates and renders for different objects. Like if you have a class for your player or something, you might want a function for updating it and a function for rendering it, so you could do it separately, and then your update code doesn't have to be reordered if you want to reorder your rendering. Now that we have the basics down, we can get into the crazy stuff that is actually making a game. The first thing we'll probably want is a player. So I'm going to do this in the object-oriented way from the beginning, which hopefully keeps us from having to rework things later. So the way we're going to do this is I'm going to create a new folder and call it scripts, and this is where everything that isn't the main game script will go. So in here I will create an entities script, and this will be responsible for a couple things. So let's just start with a basic entity class. I'm going to call it a physics entity because later on here it will be capable of handling physics. So let's define the initialization function. Let's take the game as a parameter, and that way anything that's in the game is accessible through the entity. This is a bit of a trick you can use to deal with scope issues for games. The weird thing about games compared to other types of programming problems, I guess, is that in games, it's very common for elements to interact with a ton of other elements. Some people handle these interactions through intermediary systems, but that adds more code and in some cases more complexity. It can help keep things organized if you do it that way. But if you're working by yourself, interacting with other things directly is usually a decent way to go. You just have to kind of keep track of things, and if you lose track of things, it might get a little bit tricky to debug stuff. But overall, this is a quick and easy to understand solution for scope issues. So aside from the reference to the overall game so that it can access everything in the game, we also want to take the entity type. We won't really be using this yet, but we will use it later. We also want to take a position to spawn the entity in, and then we also want a size for the entity. So let's do self.game equals game, and self.eType equals e. Actually, let's just do type. eType. There we go. The reason why I don't want to use just type here is because that's a built-in function, but using it as an attribute is fine. That doesn't override it. Alright, self.position equals position, and actually something interesting to do here is to actually just call the list function on that. It'll convert any iterable into a list, and the reasoning for that is two things. First of all, if you did pass it a list, you don't want to have a reference to that list. Let's say you spawned like 3 entities in the same location, and you passed a list in. So all of those entities could be, and this is a bit of a more complex Python topic, all those entities could be referencing that same list that represents that position. And if one updates it, all of those entities will have their position changed. So you want to make sure that each entity has its own list for its position. The other thing is that if you pass in a tuple, you can't change individual values in a tuple. You have to just update the whole thing. So it's easier to work with lists for a position because you're usually changing the position. Another thing you could be doing is converting those locations into Pygame's vector2s. I won't get into that, but there is a lot of useful functionality there if you want to use that. So let's do self.size equals size, and then we'll make an update function that just gets called every frame, def update self, and let's take in a movement variable. We'll update these arguments later and add in a tile map for collisions, but for now we just want to do movement. Something else we're going to want is a velocity. So we can do self.velocity. We don't want that. Equals 0, 0. So if you didn't know, the derivative of position is velocity, and the derivative of velocity is acceleration, so the relationships are similar. Velocity is just used to represent the rate of change in the position. So if your velocity is 5 in the x, you'll move like 5 in position in x every frame. And then acceleration, which we will also be using, will be the rate of change in velocity. You'll be updating the velocity every frame a certain amount based on the acceleration. And fortunately for us, our acceleration is going to be constant. It will just be the force of gravity. A lot of people get confused as to how they're supposed to implement like good jumping mechanics, but if you actually just use the physics formulas for how these things are supposed to work, not all of them, but the basic ones for like position, velocity, and acceleration, you can get some pretty good results. In higher level physics systems, a lot of times they will use physical concepts like force and momentum and inertia and all sorts of stuff like that, but we don't have to get into that here. Once you get to that level of physics, a lot of things actually start to feel a little bit clunky if you're not very careful about how you deal with momentum and stuff. So I actually like to work at this kind of simplified physics level. So you get the benefits of nice, smooth movement, but it doesn't feel clunky. Anyways, moving on. From here, we want to generate how much of a movement we want to make for the frame. So frame movement equals movement 0 plus self.velocity 0, movement 1 plus self.velocity 1. So what we're doing here is we're creating just a vector that represents how much the entity should be moved in this frame based on how much we want to force it to move in this particular frame, plus however much there already is in velocity. So you want kind of multiple controls on how things move, which we'll get into later. But for example, the gravity will be applying an acceleration to the velocity, and that velocity will pass through as well to the position. But for example, for moving right and left, you want that to be instantaneous usually. Or at least that's what I like it to be. So for that, we use 2 different inputs for movement. So in order to actually move it, we can just do self.position 0 plus equals frame movement 0. Typically when I have a list of 2 values that represents something dimensionally, it's going to be the first one's x and the second one's y. So position and velocity. Doing this is just updating our x position based on the frame movement, and then we can do the same thing for y. It's important that these are separate. We'll get into this with the physics later, but you actually do the movement steps in 2 stages. You do one for each dimension. You can actually do this in 3 dimensions if you want, but I'll also get to that later. Anyways, we have our movement working. So now we can do our rendering, self.render, and then we want to take our destination surface, and let's just say surf.blit, and we need an image. I'm just going to write something in and we'll fill it out later. So self.game.assets, and let's just say player, self.position. All right, so we have our physics entity here. Let's go over to game and import it. We also do have to fill out this assets thing. So we can go over here, we can do import scripts.entities. Actually, it's from scripts.entities import just that object. That's all we want from there. And we can just define our player. Self.player equals physics entity, and then just pass in the game. We'll call it player, and let's spawn it at 50/50. And give it a size of 8 by 15. All right, so we have all this other stuff going on here that we don't need anymore. So there's this image loading stuff for the cloud and all that collision stuff. We don't need that anymore. That was just demonstrational. We'll use a lot of those ideas here in a moment, but we don't need that for our actual game here. So in here, we'll want to do a couple things. So we'll want to do self.player.update, and actually, hold on, there's the movement stuff back here, which we should probably leave. Well, we want this movement variable because that's still taking our input. But for the rest of the stuff, we can do self.player.update, and then we can do the whole movement, self.movement 1 minus self.movement 0. And then for the second part, we can just throw in 0. We don't want any changes on the y-axis, because if you're in a platformer, you run right and left, not up and down. So the other part of this is to change these up and down keys to right and left. So we can do right, left. Actually, I think it's the other way around. Right? Yeah. So it's left, right. Right, so just copy these down. And that should do that. Do self.player.render onto self.screen. So the player's rendering, the player's updating, and moving. The only thing is we need to get the assets in. So for this, I'm going to start creating some utility code. So let's call this utils. So in here, we're going to want to create just a basic function. We'll create more functions built on this later for just loading images. So def load image, and we'll give it a path. And we can say our base image path is data/images. All of our images should be under that folder. So we can do image equals pygame.image.load, and it should be the base image path plus this extra thing that we're giving it. And this is where we'll want to do something new. We want to use .convert on the image. This converts the internal representation of this image in Pygame and makes it more efficient for rendering. A lot of new users forget to do this or don't know about it, and it costs them a lot in performance. So it's important to do this. There's almost no reason not to, so I just do it by default for just about everything. All right, so let's do image.set color key, and then if you remember, all of our backgrounds are black, so black will become transparent. And then we just want to return our image. So we can take this function and use it to start loading stuff. So let's go back over here, and we can do from scripts.utils import, and we want our load image function. So in here, we can finally define that one image that we needed for the player, which is self.assets equals, and then we can do player, and then we can do a load image on entities/player.png. So if you remember, there is that base images path, so that'll go data images, and then we have entities, and we go to player.png, which is this one right here. It's a bit small, but yeah. So if you're a bit lost on how I'm accessing everything from everywhere, I recommend taking a moment to read through everything and make sure you understand how everything's connected. One of the big things that's important to do when you're learning stuff like that is to make sure you fully understand things and one of the best ways to do that is to actually play around with things and see how things work when you start changing stuff. So before moving on, assuming this actually works, so I'm double checking that. I made a mistake here. This is pygame.image.load. And that's why I put that clause that it needs to work. Anyways, so this works. The player can move right and left by just pressing right and left. And we have our character on the screen. It's represented as an object, which is nice. So this is all great. But yeah, as I was saying, it's really good to mess around with things and get a full understanding of how this stuff works by changing stuff and seeing how it interacts. If you just copy everything I'm doing and don't play around with it too much, you're going to get a bit lost. I do recommend if you do end up breaking something and you're not sure where you went wrong, you can go back to the last available reference code that I have on the assets page for this tutorial. So you can always have some baseline that's working while following this. Anyways, so now that we have movement and our player, the next thing is to deal with the fact that we have some pixel art here and it's really small, we can barely see it. So this is where we use an interesting technique. There are multiple ways to do this. Pygame has some built-in stuff for scaling, but you get a little bit more control if you do it yourself. And by do it yourself, I mean what I'm about to get into here. It's a bit slower performance-wise, but it's pretty much a non-issue at this resolution. So we can do self.display equals pygame.surface. And this is another conventional name that I just started using at some point. I think I got this. I don't know if I came up with display or what. I don't know where that came from. But for me, screen's always been kind of the window surface, and then display is the one that I actually render onto. All right, so we have these two surfaces. If you notice, display is half the resolution of the screen. And also I use a new function here, which is the pygame.surface function. Pygame.surface generates an empty surface. So like an empty image. It's like you loaded an image of this dimension using pygame.image.load, except it's all black by default. So just imagine a black image 320 by 240, and that's what pygame.surface does. This is useful for just creating stuff in memory that you might need for some kind of purpose. In my case, the display is going to be a second surface that we use for rendering. So the idea is to render onto the smaller display and then scale it up to the screen, so that you render on a small resolution and then you scale it up, which creates the pixel art effect. So let's render everything onto this display. To do that, we just swap all this to the display. And then the last step right here, because actually I can show you what happens, you just get a black screen. Because now that we're running on the display instead of the screen, you get nothing. So we have to render onto the screen. So screen.blit, and we want to blit the display onto the screen. So if you do this, we now get this. So it's just shrunk. So the next step is to scale it. So this is also something new. We'll do pygame.transform.scale, and the first argument is the surface you want to scale, and the second one is the new size. So what we'll do is self.screen.getSize. So we're scaling this surface to the size of this one. You could pass in like a tuple of any size you want, but it's convenient to just use the get size on the screen here. So the return value of this will be the scaled display, and we can just throw it on the screen, and that's what we're looking for. All right, so now you can see the pixel art has gotten a bit bigger, and it actually looks like pixel art. All right, now this is where things start to get crazy. We're gonna get into tiles and physics. Well, we've already done a little bit of physics in the sense that we've implemented some code for velocity. We're not using it yet, but it is there. So we'll want to create a new tile map script. Tilemap.py is what we'll call it. And in here, we'll want to create a new class. We'll call it tilemap def init. And then we'll want to take like a tile size. We'll say 16. And that 16 is a default value. We'll say our tile size is equal to the tile size. Self.tilemap equals that. And self.offGrid tiles equals this. All right, so what we're doing here is we want two systems of tiles. So we have the tile map, which is where every single tile is on a grid. So it's just a square grid of a bunch of tiles. And then the off-grid tiles are things that we placed all over the place that might not line up with the grid. So the idea is that you can only handle physics with this grid here. It's more convenient to work with. You could add a physics here if you wanted, but if you keep stuff on a grid, it's easier to optimize it. So we'll have most of our tiles on this grid in here. And so there's a reason why this one's a dictionary and this one's a list though. So we're going to do something where we map each tile based on its location. If you've done any of this stuff before, you may have seen like an example of a map where you do say there's a little hill or something. So if you have a little hill you're mapping, maybe you would do something like this, where you have 3 rows in a list and your ones represent the ground. So you get a little hill of the ones right here, and there's a slight issue with this approach. Let's say you wanted 2 islands that are far apart. You have to fill in the space between those islands with air. So if a lot of your world is air, you're going to have a lot of wasted space in your setup here. And you also have to go through all of the work of creating that space between the tiles as well. So the approach that I like to use instead of just throwing things into a list, because you can't have 2 elements at different locations without having all of the elements between. The technique I like to use is to create something where you have, let's say, a tile at the location 0, 0, and we say it's like grass or something like that. And maybe a tile at 0, 1 called dirt. And the advantage here is that you could have a tile at 9,999, and that could also be grass. And you don't have to fill in all that space between. So this is really convenient to work with. It's still also very efficient to look up tiles based on location. We'll be using a slightly different strategy here. You can use tuples like this as your location for your tiles, but I will be writing these as strings, so I'll use like 0, 0 or 0, 1 and stuff like that. And that's because of the way the files will get saved. I'll get to that in, I don't know, maybe an hour, but it's a lot easier for this use case to do it as strings because the format we're going to save these in doesn't support tuples. In my own framework, I added a system where I can convert tuples into something else so I can work with tuples because they are easier to work with in terms of the actual code, but I don't want to mess with the export stuff. All right, so let's throw in some basic tiles for us to work with. We can do for I in range 10, and we'll create a couple different tiles. So self.tilemap string of 3 plus I plus, we'll do 10 equals type, and we're going to get it a little bit more complex with our tiles here. Type grass, variant 1, position 3 plus I 10. So there's a couple things to note here. First of all, our tile will now be represented as this dictionary. So that way our tile can have multiple attributes. You could implement this as an object if you wanted, and you could do like a tile like that, but I'm not going to go through all that effort, so we're just going to use the dictionary. This dictionary will have the type, the variant, so within grass there's a few different types of grass tiles depending on like what directions are air and stuff like that. And then I'm also storing the position in here, and that's because this position as a string is not easily usable because you would have to split it by the semicolon, convert it to an integer and stuff like that. So leaving one in here that's actually as a tuple of integers is easier to work with and actually faster. So that's useful to leave there. We'll be using that later. And then this is just concatenating the dynamic location based on this iteration with a fixed position of 10. So this is going to be the positions of 3 through 12 on the X and then 10 on the Y. So this will be a horizontal line of grass tiles. All right, so let's copy this and we'll do it again, but we want a horizontal line now. So for that, we can delete this. There's a semicolon on the other side and do cluster I plus 5. And then instead of grass, we'll type stone. And then this position needs to be updated. The position here should match the one here. So we do 10, 5 plus I, or rather I plus 5. And then we can, actually this one's inconsistent, so we do 5 plus I over here. All right. So we now have our tiles, but we need a way to render them. In order to render our tiles, we'll need something to render. So we'll have to go over to our utils and create a function for loading multiple tiles at once. Because if you look over here in our data, and we go to images, tiles, let's say grass, there's a bunch of images here. We don't want to type all of those out. We want that to load automatically. In reality, you could create a function to just load every single image in that directory automatically, which is what I normally do in my games. But we'll just be handling a single folder for now, and then we'll just load all those individual folders. All right, so we can create a def load images function. We'll give it a path. Do images equals that for image name, and then we'll have to import a new library here. We'll do import OS. So this is all we're going to do here is do os.list dir. We'll take the base image path plus path, and then I'll pass here for now. So os.list dir will take a path and give you all of the files that are in that path. So specifically here, if we ask for, say, images, tiles, and we go grass, it'll give us the 0 through 8 images. So this is a way to easily dynamically load images. So let's go ahead and say images append, and then we can actually use our other function here, load image, and we give it the path plus slash and then plus image name. So remember, this is the path to the folder, but not including the base image path. That's why we don't have to add it again here, because this also includes it. So yeah, this is path to the folder. We add a slash because we want to get something inside that folder, and then we do the image name, which is given by this function here. All right, so since this will return the loaded image, this images list will become a list of all of our loaded images. So we can just return that, and now we can use this to start loading some stuff. So let's go back over here into the game, and in our assets we'll want to load a couple things. So we have several tile sets in here, or not several, but a few. Let's do decor, that's one of them. We'll do load images tiles / decor. You could do this in a for loop if you wanted. Actually, we need to import that up here also from utils. But yeah, we could do this as a for loop if you wanted, but since there's only 4 of them, I'm just going to copy paste. So we have grass, we have large, decor, and we have stone. All right. So let's take the grass, throw it over here, large decor, throw it over here, stone, throw it over here. All right. So if I do that, and then if I just do print self.assets, we can actually see all of our assets if I run the game. All right. So if you look in here, we have our assets. So you can see we have decor, and it's got a list of a bunch of assets. And these are just how Pygame represents these surfaces if you print them out. So it lists all of the surfaces we have and all of our different tile sets, like grass right there. All right, so now that we have those assets, we can start rendering our tile map. To do that, we do def render self surf, so that's our destination. And actually something else we want to take up here is probably the game. So we can do self.game. That way we can pull our assets. So if you remember correctly, I mentioned that we have these tiles and these tiles. These ones are on the grid. These are the only ones I filled out for now. I'll get into these when I do the level editor later, but I'm going to write the renderer for both right here. So let's start with the stuff on grid, which is what we have working right now. We have for location in self.tilemap. So when you iterate over a dictionary, you'll get all of the keys. So that'll be these values. So we'll get like 3 and 310, for example. But to get the actual tile, we'll have to look it up in the dictionary based on the key. So that'll be self.tilemap location, and that'll give us this part. All right, so from here, we can render it. So we can do surf.blit, and we'll do self.game.assets, and then this is where things get a bit tricky. We do tile type. So if you remember correctly, over here, we gave these things names. So in this dictionary, we have, I'll do this print here. In this dictionary, we have grass, and then it's a list. So if we go over here, if you remember, we have grass. So we want to say we're looking for those images of the grass category, and variant will be the index of the image we want to use from there. So from here, we can do another indexing on this assets thing. So this gets a little bit confusing. You can like print it out at this state if you want to see what you're looking at, but From here, we can do tile variant to index based on this and get the very specific image that we're looking for. From here, we can go ahead and handle the position for the rendering. So that's just going to be the position of the tile, which we have up here already. And then something you have to do here is you have to multiply by the tile size, because these coordinates are in terms of the grid. So the grid has tiles of a specific size, and to get this in terms of pixels, because that's how rendering works, we'll have to convert it using the tile size. So self.tile size, and then we do tile position 1 by self.tile size. All right, so that is a very long line of code, but it should cover all that we need for that rendering. Something else that I just remembered is that this might not work on Linux. This function right here behaves differently on different operating systems. I believe on Linux, the order of the files you get is different from Windows. On Windows, it's alphabetical. And it might be alphabetical on Linux and just in a different way, I forgot. But if you go over here, we're depending on the assumption that it'll load 0 as the first one and 8 as the last one. So that might not be the case. So what you have to do is if you just run this through sorted, it'll sort it for you, and then that makes it consistent between all operating systems. Something else you have to be careful about is that since we're depending on the file names here and it's alphabetical, 10 actually comes before 8 because it'll look at 1, 0 and it'll throw it either before or after the image number 1, because that's how it's sorted alphabetically. So the way you deal with that is you pad the front with zeros. So if you look at the entities here and say go to the idle animation, you can see I padded the front with zeros. That way 10 is no longer before 8. So that's how you can keep that consistent. This is abusing a little bit of a trick to keep our images in order here. Anyways, so back to the tile map. The last step for rendering is to handle the off-grid tiles. These ones are going to be the same tile data, but they're not going to be organized the same way. So for tile in self.offGrid tiles. So this will be, for example, we could actually just dump this one in here and say that's an example of what we could have for the off-grid tiles. So it's just, we have that same type of tile object in there. It's just a list instead. The one thing to note that's going to be different is that this position will be interpreted as pixels instead of a grid position. And that's because, well, the whole point of this is to be able to put things off of the grid, whereas the tile map is supposed to be on the grid. So the coordinate system is going to be a bit different, so we don't have to do that multiplication with the tile size. So we just do surf.blit, and then we can grab the same thing right here, and then it'll just be the tile position, since that's already in pixels for this set of tiles. All right, so we have our tile map, so let's go ahead and load it in. For that, we can just do from scripts.tilemap import tilemap, and then we can go over here and say our tile map is equal to that, and then just for the sake of it, we'll say that tile size is 16, even though that's already the default, just because for clarity. You could change this if you want. So next step is to render it. In our case, we want the tile map to be rendered behind the player, so we'll do self.tilemap.render, and then we want self.display is where it'll go. And something else I just thought about, speaking of layering, is that we probably want our off-grid tiles to be behind the grid tiles, because in our use case, the things that we're going to be placing off of the grid are mostly decorations, and the things that are going to be on the grid are mostly going to be tiles you can like run into and physically collide with. So because of that, the decorations are normally something that go in the back. So you usually want to render these first if you're using this technique. So we can go over here and throw them right there so that they get rendered first, and that means that these tiles you collide with are in front. You don't want to be walking and you see like some sort of decoration, it blocks the view of a tile and you just run into something for unknown reason. So that should be good enough for now. Let's run it and see what we get. We got an error because I forgot to pass in the game. So we do self, that'll pass in the game reference so that it has access to the assets. And there we go, we have our tile map. And we can see our tiles, which look nice. So now let's make it so that the player can fall, because right now we can only move right and left. So for that, we go over here. And since later on we'll create a player entity that will inherit from this physics entity, but because gravity will be universally applied, I'll apply it to this physics entity object instead of creating the player one. So for now, the player can still be a physics entity. All right, so let's go ahead and apply our gravity. So to do that, as I mentioned, you apply acceleration by modifying velocity. So our velocity is going to be self.velocity, and the y-axis of the velocity is the second value. So right here, normally you could just do plus equals, say 0.5 or something, but I'm going to use a different trick because there's this idea of terminal velocity in physics. So in physics, something will have a maximum velocity it can reach while it's falling, and that's called terminal velocity. You don't want to just fall a long distance and just accelerate to an infinity because you keep falling. So for that, you usually want to cap how fast you can fall after a certain point. You want it to kind of ease into that fall, but you also want a cap. So for that, we can use the min function, which is a built-in Python function. It'll take the lower of two values, or however many values you give it. Let's do 5. That'll be our maximum velocity downwards. Remember, since this isn't the normal coordinate system from math, we have positive y is down, not up. So that might be a bit misleading, but that's how it works. So this 5 represents a maximum velocity of 5 downwards. You can go more than 5 upwards, which would be like -10 or something. So that doesn't affect this. So we take 5 and then we do self.velocity 1 plus 0.1. So right here, we're modifying the velocity. And then if this modified velocity is less than 5, it'll take this part. So that's just effectively doing a self.velocity 1 plus equals 0.1 if that's the case. But in the event that this number is smaller, it'll take this one instead so that it can't go over 5. I'll use this technique a lot later on, but I figured I'd explain it now since it's a very useful technique. All right, so we have our velocity being updated. I'm actually going to drop this below the movement. And then now if we run the game, look at that, our player falls. But he falls through the floor. So now is the time for physics. This can be a bit tricky if you don't know the actual technique for doing these types of collisions. I remember I spent like a year or so on game development. Actually, I think maybe a couple years before I heard about this technique. And I actually just found it in some example code somewhere. I don't even remember where I got it from. But trying to write your own stuff for this from scratch is a bit tricky if you don't happen to know the technique for having consistent collisions. All right, so in order to handle collisions efficiently, what we'll want is a way to look up tiles. So for physics, in the case of the player, since it's not very large, you just kind of want the tiles that are nearby the player, and then you can run the collisions from there. You don't want to look up all of the tiles and test them all for collision with the player, because we know the player's position, and we can look up the tiles based on position. So there's no reason to try to test all of those collisions at once if we can just look up the 9 tiles around the player. If the player were bigger and could collide with a larger area, you'd want to look up more tiles. So keep that in mind if you're doing your own stuff here. But in our case, we just need the 9 neighboring tiles and we can get some pretty good physics. So let's do neighbor offsets equals -1, 0. These are going to be the offsets from a given tile to get the 9 tiles around and including it. So -1, -1, 0, -1, 1, -1, 1, 0, 0, 0, -1, 1, 0, 1, 1, 1. All right, so these are just all of the combinations or all the permutations of -1 through 1. Actually, this should be offsets, not offset. So now we can write an interesting function. We can do def tiles around self position. So you pass in a pixel position. So remember, the grid tiles are not in pixels, so we'll have to do a bit of a trick here. So we'll have to convert this pixel position into a grid position. To do that, we can do tile location equals int position 0 self.tile size. So if you don't know what this double slash is, it's integer division. So it'll chop off the remainder so that you don't get, for example, if you divide 3 by 2, you don't get 1.5. You would get 1. And you might be wondering, if we're doing integer division already, why do we need this int here? And that's because if one of these numbers is a float, it may round it to an integer, but it'll still have the .0 on the end, and that can cause some problems with the way we will do indexing in a moment. So we still have to convert it to an integer. And you might be wondering, okay, so if we're already converting it to an integer, why can't we just chop off that extra slash and do normal division and then convert it to an integer? Well, the problem there is that integer truncates. it does not do proper integer conversion the same way that double slash does. So for example, they handle negative numbers differently. Let me pull up a terminal so you can see this. So let's say you have 3 divided by 2, you get 1. Let's say you have int 3 divided by 2, you also get 1, so that's expected. But let's say you have negative 3 divided by 2, you get negative 2. You do int negative 3 divided by 2, you get negative 1. They have different results, and that's because they handle negative numbers differently. So int will pretty much just chop off, like if you did negative 3 divided by 2, it'll pretty much just chop off that 0.5, which is not a consistent behavior, because if you think about the number 0 through, actually negative 1, everything between not including negative 1 and 1, so let's say 0.9, that will go to 0. Negative 0.9, that will also go to 0. So that's an important distinction, and this is why you need to be very careful about converting things to integers when dealing with computer graphics. This is making the space of 0 almost the size, or sorry, it's the same space between like 1 and 3. In terms of pixels, I guess, you could say that the 2 pixels bordering 0 get brought into 1 or something like that. It causes some issues when you're dealing with this stuff, so especially when you're dealing with grids, you have to be very careful about how your stuff gets rounded. Anyways, back to what I was doing. So this mess of code will convert the pixel position into a grid position. So that's just the x-axis, so we have to do the y-axis now. And now that we have both, we have a nice tile location, and then we can do a for loop. So for offset in neighbor offsets, this is the thing I defined earlier, we can now generate all of the tiles that are around this pixel position given. So for this, we can do check location is, and then we compose a string, because that's how we did our keys here. String of tile location 0, and then we do plus offset 0. So we're adding all of these numbers to whatever this base location is, so that'll give the 9 tiles in that area. So we do that, and then we add our semicolon, because that's what's our location, and then we can do it again, and we'll throw it that, which is the y-axis. All right, now that we have our string, we can do if check location is in self.tilemap. That just checks to make sure that there is a tile that happens to actually be there, because remember, in a tile map we can have a lot of empty space, and that's just denoted as there not being anything in the dictionary for that location. All right, if that location exists in the tile map, we can do, actually, I'll throw a pass right here right now, and then we can go up here and we'll do tiles equals this. This is the tiles we're returning, so we can do tiles.append, and then we can just grab the tile data by doing self.tilemap and then check the location. All right, so now we can return the tiles, and this will give us all of the tiles around that location. So I'm just gonna run this function so you can see the output here. So let's just do print self.player, actually no, self.tilemap.tiles around, and then we can do self.player.position. So that'll give us some interesting output here. You see that? So right when we passed to the ground, it started outputting this data here. So when we're in the air, it just gives us this. And then when we're near the tiles, it gives us this. So this doesn't mean we're touching those tiles, it just means we're near them. And this is where we can actually do the collisions, because that's a little bit slower than looking them up. All right, for the collisions, we gotta go back to tile map, and there's something else we gotta do, because we don't want to collide with all of the tiles. We want to be able to put stuff in the world that we can see, but we don't necessarily have physics for, so you can just like walk by a tree or something. So the next thing we have to do is add a function that'll filter the nearby tiles for things that have physics enabled. So let's do physics rex around. So we'll do another step in here to make the collisions easier, which is converting all of these tiles that have physics into pygame.rect. If you remember, that's what we did the collisions on, like, I don't know, an hour ago. So we can do rex equals this. This is the rectangles we're returning. And then we can use this function here to get all the nearby tiles. So we can do for tile in self dot, and then we do that, and get rid of that self. And now we're iterating over all of the nearby tiles. If there are none, this whole loop gets skipped to begin with. So we would just return this empty list of recs. So if tile type, and this is where we're going to get into something interesting, we need to add a list of things we want physics on. So physics tiles equals, and I'll say grass and stone. So if you don't know, even though curly braces are normally for dictionaries, if you don't do the key value pair thing, this is what's called a set. A set is used for a collection of values. Usually order is not important, but the big thing is that no duplicates are allowed, and actually looking up to see if a value is in a set is more efficient than looking up a value to see if it's in a list, for example. So this is actually slower than doing this if you're looking to see if a value is in there. So for something that's being run a lot, which is checking tile types, it's good to have a set there. And this is one of the techniques you can use to optimize things. And don't forget that we also have this code right here, which is also already a huge optimization. You can have as many tiles as you want, and the collisions will still run fast because it just looks up the nearby tiles. If you don't know, looking up a value in a dictionary is also very fast. You can have as many values as you want, and it still roughly takes the same amount of time to look up a value as long as you know the key. All right, so we want to check if our tile type is in the physics tiles. So if it's in physics tiles, that's very English, then we know that this tile that we have near us is a tile that we can collide with. So because of that, we now want to add something to our rects list. So we just do a dot append, and up here we're going to have to import Pygame so we can actually create a rect. We can do pygame.rect, so a new rectangle. And remember, rects are just kind of a thing in memory unless you decide to draw them, but you can run collisions on them, you can draw them, you can do lots of stuff with them. So we'll create it with the x position being the tile's position on the x-axis, and you have to multiply it by the tile size to get the position in pixels, and then tile position on the y-axis, get the pixel position, and then we also need the tile size because this will be the size of the tile in width and height. And since they're square, it's going to be the same for both of them. All right. So that will add the new rectangle, so we can return these rects. And if I go over here, and if I take this back and then do physics rects around, instead of returning those tiles, it should return a bunch of rects when I pass through. All right, so you see these? These are the rects that I'm nearby. So the final step here is to run the actual collision detection and handle the collisions so that the player can't pass through. For that part, we'll go over to our entities. And we'll have to do a new step here. We're going to throw in the tile map. So tile map will become an argument, and we can go back to game, and in our update function right here, we can do self.tilemap so that that gets passed in correctly. All right, so now that we have access to our tile map in here, we can do our collision detection. If you remember from before, in order to do collisions, you have to have two rectangles. So the thing you're colliding with needs a rectangle, and the thing that's doing the colliding needs a rectangle. So let's give the physics entity a rect. So to do that, we want one generated dynamically because we don't want to go through the effort of updating it all the time. So we will create a function for generating it. Let's do return pygame.rect, and we'll do self.position0, self.position1, so that's the top left. And that's something important to note, is that we're using the position as the top left of the entity. If you remember, that's how surfaces are blended onto each other. It's by top left. And that's also how we're going to handle the physics here. So this position on the entity, you might think it's the center, but it's actually the top left of our entity. All right, so now that we need our size, which we already have, self.size0, self.size1, and that will be our rect. And the reason we want the function is because we're changing this position all the time, and we want to be able to get a fresh rect based on that new position whenever we need it. All right, so now with that rect, we can finally do our collisions. So let's split this in half here. We'll do entity rect equals self.rect. And then for rect in, and this is where the magic is, tilemap.physics rects around self.position. We want all those nearby tiles. If entity rect.collide rect with one of those tile rectangles, this means that we've had a collision. So now the next step is to handle this collision. So this is where the magic of splitting up our movement into two axes comes into play. You don't want to do them both at once. I have a whole video about this. It's pretty old, but it's still a really good video, I think, explaining in depth how this technique works. But the idea is that if you handle one axis at a time, say you move on just the x-axis, if you collide with a rect, because you know the player is a rect and the thing you collided with is a rect, and you know what your movement was, you can now resolve that collision by adjusting the player's position based on what was collided with. So in this case, let's say you're moving right, you collided with a tile, so this is where this thing comes into play. We could say if frame movement 0 is greater than 0, that means you're moving right. Let's say you're moving right, you collided with a tile. So there's a really simple solution for how you handle this. You make the right edge of the entity snap to the left edge of the tile. So that way they touch and then they get pushed back straight to the edge. So we just do entity rect.right equals rect.left. And we can do if frame movement 0 is less than 0, entity rect.left equals rect.right. Because let's say you're moving left, because remember negative x is left. If we're moving left and we collide, we want to set the left side of our entity to the right side of the tile. And the last thing you have to be careful of here is that we're modifying this rect's position. We're not modifying the player's position. So we have to go and update the player's position now based on this logic we did here. So if you want to do the actual math yourself, it gets more complicated. That's why we abstracted out to the rects. So we can do self.position 0 equals entity rect.x. So you might be wondering, if you can move around a rect like this, then why don't we use the rect to represent the position of the entity? So there's a slight issue with rects. If I import Pygame here, I can show you. You could do pygame.rect. So let's say you have 0, 0, and say 10 by 15.5. Rects only work with integers. So you can't have subpixel movements with rects. So depending on how fast something is moving, you might have problems with movement depending on whether or not you're abstracting for a rect or not. There are very few cases where it's okay to just have your position represented as purely an integer. When it renders, because we're using pixels and everything, it gets converted into an integer. But for example, if you move 0.5 pixels, here I can show you. Let's say r equals pygame.rect, you can do r.x plus equals 1. r.x is now 1, or you can just print it out. And now let's say this, r.x minus equals 0.5. That works fine, so r.x plus equals 0.5. Now you see the problem. We just added 0.5 and it didn't move. So let's add it 2 more times. It still didn't move, and this is where the problem is. So if you're using Pygame CE, which is that choice I mentioned at the beginning, there is something called an frect, which allows the rects to be floats, so you can still do collisions with them and handle positions. But since I'm trying to make this tutorial work for both versions of Pygame, I have to create my own position variable here. That's why we do all of this. It's a bit tedious, but that's how it is. So if we were actually just purely doing a Pygame CE tutorial, I could make this a couple steps simpler and take out the position thing, but I'm not doing that, so it's a bit more complicated. All right, so we've done the collisions for the x-axis, and now we do the y-axis. And this is the whole point of separating out the movement here, because you handle the collision twice per frame, so that you can handle the collisions based on whether or not that collision was from moving right and left or up and down, because it gets a lot more tricky if you try to do both of them at once. All right, so let's just copy this over, and we do the same thing. The only difference is this is now the y-axis. So this now becomes the bottom and top and bottom. So if you're curious about what these attributes actually return, this is just a single integer representing the x or y axis, depending on whether or not you're doing top, bottom, or right and left. So it'll be like a position on the x-axis or a position on the y-axis. All right, so now with those two collisions done, we have our physics. So let's go ahead and run this and see if it works. And look at that, we're standing on the ground. And I can move around, and I can run into this wall, and I can't pass through it. So now there's a slight problem. You see, I dropped off very quickly there. I didn't slowly accelerate into a fall like it should. So the other thing we have to keep track of is the fact that our velocity here reached 5, but there's nothing to ever bring it back down. Normally when you hit the ground, your velocity should be updated to 0. It may not be able to move through the tiles because of our physics, but that velocity is still sitting there at 5. So let's add something to keep track of what types of collisions we've had. So I'll go up here and add a self.collisions dictionary, and we'll do up, false, down, false, right, false, left, false. So this is a little nice trick you can use to keep track of which directions you've had a collision. And we can use it in here and in other locations to see what directions an entity just collided with. This will be useful for things like wall jumping and stuff later. So for our collisions here, we just have to go into here, and when we actually resolve these collisions, we can update our collisions. So self.collisions right equals true. And then this one is going to be left. And this one will be down. And the last one is up. All right, so we have our 4 directions. And something important to note is that we're resetting it every frame. Every single time this update function is called, this will be reset. So it'll be 1 frame you get where it says true after a collision. But if you're just continuously colliding, like you're holding right and you're constantly running into the wall, it'll always be true. But if you're running into a wall and you lift your finger off the right key, it will no longer say true because you're just standing next to the wall, not actively running into it. All right, so from here we can do if self.collisions down or self.collisions up. This is where we want to reset our velocity. So self.velocity 1 equals 0. So you notice I did it on down or up, and that's because if you run into the ground, it should stop you. If you are going up and you hit the roof, it should stop you. You could also do the x-axis too, but we're not using that velocity yet. We're only using the y velocity for now. So now I can run around here, and if I fall off the edge, it slowly accelerates. So let's go through here and add one more thing. It would be nice if we could jump, and this is where the magic of this whole physics-based system comes in. So we can do if event.key is pygame.k_up. We can do pygame or self.player.velocity1 equals -3. So all we have to do is override that vertical velocity and set it to a negative number so that the velocity is pointing upwards, and suddenly the player is just moving upwards, and then the gravity will pull it back down. So it's a nice smooth jump. All right, so if we run this code, and if I press up, you can see I go up and down. So it's a nice arc. And it's very responsive as well. This is, I think, the best way to do jumping. There are some people that try to like model it as some sort of formula or something, but overall I think this just works really well. And this is a technique that I always use. All right, so now that we have jumping, we can test a couple other things. So right now we have infinite jumps. Later we'll work on making that limited, but for now we have infinite jumps. The last thing we need to test is to make sure that if I hit my head, it stops me properly. So if I go up here, you can see I instantaneously bounce off the roof. I don't run into it and stick. So that should be pretty much everything for the physics. If you see, I can just run around and this works pretty much exactly as you'd expect, which is great. So we have a game where the player can jump and run around and run into stuff, but the next thing that you would often see in platformers is a camera that can move around. So let's get into that. The idea of a camera when it comes to lower level computer graphics is really just an illusion. Instead of moving a camera around, you're really just moving everything else. Let's say you wanted to move the camera right. If you moved everything in the world to the left, you would see the same thing. So this idea of a camera isn't really real. You can abstract your code that does move things around into like a camera object, and that's sort of what we'll be doing, and that's how you can sort of get something that's easy to work with so you can move the camera around. Alright, so to do this I use this idea of a scroll variable. You can think of this as like the camera's location. So self.scroll equals 0, 0. So let's start the camera at the position 0, 0. The next thing we'll want to do is actually make it so that this camera position gets applied. To apply this camera position, we need to start adding offset variables to everything that renders. So right here, let's do offset equals scroll. And this is how much we're going to move what we're rendering, because as I mentioned, the idea of moving a camera is just moving everything else. So we'll add this offset for rendering based on where the camera is. And then we can add this, actually it should be self.scroll. We can add this to all of our rendering stuff, which is just, I believe, these two things. So our tile map and our player. Now, go over to tile map, we go into render, we can say offset equals, and we can give it a default value in case we don't provide it, but we did, so whatever. But over here, we're going to want to apply this offset. So we do minus offset 0, tile position 1 minus offset 1. You'll notice I broke up this tuple that was here, or it was originally just the position, but I had to break it up into its elements so that I could adjust it. If we were using Pygame's vector tools, you could just add it or something. Something else to note is that I'm actually using subtraction here. Instead of adding the offset, which is a bit more intuitive, I'm subtracting it, because when you actually are working with the camera, if you remember I said you move the camera to the right, everything on the screen effectively moves to the left. So if you want to deal with the camera in world coordinates, the offset should be applied negatively. Alright, so now we have to do that over here. So we can go minus offset 0, minus offset 1. Okay, now that we have offsets in here, let's go over to the player. And in here, take the offset parameter. And then we also have to output it here. Offset 0, self.position 1, minus offset 1. Okay, now that we have that, if we run the game, it shouldn't crash, and we see the exact same thing. The next step is to make it so that we actually are moving our camera. To do that, we can do something as simple as self.scroll 0 plus equals 1, and then we can run the game again, and you can see the camera's moving to the right. So now let's do something where the camera focuses on the player. We're going to use an interesting technique here. We don't want the camera to just move linearly to the player. You want it to kind of slow down as it gets closer to the player, so it's a more smooth motion. And it should speed up the further away the player is from where the camera is. So let's do scroll 0 plus equals, well, self.scroll, and then we can do self.player.rect.center x, and then this is where things get a little bit tricky. Minus self.display.getWidth divided by 2. So this camera position is really the top left. So if you were to actually put the camera directly onto the player's location, the player would end up in the top left of the screen, and we don't want that. We want the player to be in the center of the screen. So what we have to do is we have to subtract part of the screen size so that the camera is positioned in a way where the center of what you can see is on the player. So that's what this is for. And then the next step of this formula is to subtract self.scroll 0. So if you go and do the math on this, we're taking where we want the camera to be, we're subtracting what we have, and then this whole thing is being added to the scroll. So what we're doing here is just finding how far away the camera is from where we want it to be, and then we're adding it to the scroll. So if you think about it, this is just a glorified way of setting the camera to where we want it to be. But there's a reason why I wrote this as plus equals, and we have this in parentheses here. So there's this fun trick you can do, where if you just divide the increment, because this is how far off we are, if we divide by 30, it now will take 1/30th of whatever distance there is remaining to the center, and apply that instead of the whole thing. So the further the player is, the faster it will move. And as it gets closer, it'll slow down because that distance shrinks. All right. So let's take this and do this for the y-axis as well. So it would go center y and get height and scroll 1. And there's this one minor detail we'll have to deal with here. I think I might be able to demonstrate what the issue is. You might be able to see, you might not. It's a difference of a pixel. So let's run this and see what happens. So, oh yes, you can see it. So look at the player. I'm like jittering around a bit. So if I jump especially, you can see it's jittering with the floor. The player was bouncing up and down. And that's because the player's position is a float. It's not a whole number. And because the scroll is also not a whole number, when you round things so that you can get the pixel locations of everything, though those fractions can add up and make things inconsistent depending on the subpixel movement of the camera. And we don't want that. We want the subpixel positions to not really come through in the placement of entities, because we want things to be nice and smooth for a pixel art game. If you're not doing pixel art, maybe this wouldn't be as much of an issue, but for pixel art especially, you should deal with that jittery issue. So to fix that, we just take a variable called render scroll, and we can assign it to the integer of self.scroll 0 and self.scroll 1. So it just takes whatever the scroll is and converts these two numbers to integers. If you remember before, I mentioned there was an issue with using int on pixel locations. That's not as much of an issue with the camera, because if the camera's off by 1 pixel, it's not a huge issue. If something's off by 1 tile, or depending on how things are moving, if it's off by 1 pixel, it could be an issue, but for the camera, it's not an issue. So we don't have to worry about trying to deal with the weird way the int behaves. Anyways, so now that we have this integer version of the scroll position, we can use that instead of self.scroll. And because now the scroll won't have its own decimal component, the only thing that will have a decimal component is the player. So you won't get any of that subpixel movement showing through as you show the camera, because you have to have 2 elements with subpixel parts to their coordinates for that to work, or for that to cause issues. Anyways, so if we run this again, that jitter should be gone. Now you'll notice that the camera gets a little bit choppy as it gets closer to its target. There's not much you can do about that, because the camera's position is in pixels and everything's rendered in pixels. So since our pixels are larger, since this is a pixel art game, if we want to keep things consistent, it gets a little bit choppy. Now there are some games where they'll have like pixel art artwork, but everything moves around with subpixel movements, and that's something you could use to get the movement of the camera to be a bit smoother. But I like to stick to pure pixels. I'm a bit of a Puritan when it comes to my pixel art, so that's just how I like it. Anyways, our sky is looking a bit flat, so let's add a background there. If you remember, we have our background.png here, which is a nice sky background with some patterns on it. And let's go ahead and load that in. So we can do background, load image, background.png. And now, instead of filling the screen with this color, we can do a .blit, and we can take our self.asset background, and we can put that at 0, 0. So since this background is the size of the screen, that pretty much does the job of wiping the screen for every frame. Before we were filling it with one solid color, now the screen basically gets reset to whatever this background is, because this will draw over everything that was there before. Now if we run the game again, we now have our background, but our sky is still looking a little bit empty, so why don't we add some clouds? So this is where things are going to start getting a little bit hectic. Let's go ahead and go into our scripts here and create a new script called clouds, and let's import random because I know we will be using that. Let's start by creating our cloud class. So class cloud, we need an initialization function. So a cloud will have a position, and then we'll have some kind of variant, but in our case, we'll just pass the image that we're using. And then a cloud should have a speed that it's moving at, and then a depth for how deep it is into the sky, I guess. All right, so we can do self.position equals list position. If you remember, we want to take the list of that position, so we do with tuples and copying and all that. And then we can take the image. We don't want to copy this image because we're not modifying this image in the cloud, so we can have them all pointing to the same source image so that we don't waste memory. All right, so for the speed, that will be the speed. And then one last one is the depth, which is the depth. All right, so when we update our cloud, we just have to do one thing. The cloud just has to move a little bit. So let's move the cloud based on its speed. And then let's create a render function. So self, let's say our destination surface, and this will need an offset too, because remember now we're working with the camera, so we need to start taking offsets into pretty much everything we render, unless it's like the user interface, which we won't have for this project. All right, so we need to calculate a render position. We'll do self.position 0 minus offset 0 by self.depth. So instead of just applying this offset straight up, we're going to use a trick where we multiply it by the depth. That means that if the depth is like 0.5 and the camera moves like 5 pixels to the right, this cloud will only move 2.5 pixels to the left, whereas all the terrain in the front is moving 5 pixels to the left. And that will create a nice parallax effect. And this is probably the easiest way to implement that, is just multiplying your camera. For this, we'll want all of our depths to be less than or equal to 1. In reality, we're actually going to go even lower than that, so that they move slowly in the background. Alright, so self.position 1 minus offset 1 by self.depth. And then that should cover our render position. So now we need to actually render it. So surf.blit, that's our destination surface. Self.image, that's the image for the cloud. And then we do the render position 0, and this is where some other magic comes in. If you notice here, our position just keeps on incrementing. We don't have any code for removing our clouds or adding new ones. I'm going to use a trick where you just create like a set amount of clouds and they just loop around. And to do anything that loops with computer graphics, usually you want to be using the modulo operator, because when you divide something by another number and take the remainder, you're effectively just creating a loop of numbers. So for example, if your modulo is 10 and you have your number is 5, you'll get 5 as an output. If your modulo is 10 and your number is 12, you'll get 2 as an output. So you can increment up all the way to 9, but once it hits 10, it'll go back to 0, which is really nice for making things loop. We have to do some offset stuff because of the way the images are positioned. So let's go ahead and do modulo surf.getWidth. So that's the size of the display. And we'll actually want to add some width here because you don't want the cloud to be looping as soon as it hits the edge. You need to have the extra space for it to go off the screen. So you need extra space for looping based on however big our cloud is. Otherwise, you'll see it teleport before it's actually fully off screen. Or the other thing you could end up seeing is that it suddenly appears on the left side of the screen instead of rolling onto that position. All right, so for this, we'll add self.image.getWidth. And then we'll want to subtract the width again. And that will just handle the way that images are placed on the top left, and we have to do some adjustments for the edge of the screen and for the wrapping. So now we have to do the Y component. So we can just copy this whole thing, go to the right, paste it. We can say render position 1, get height, get height, get height. All right, so now that's our mess of a rendering function done. Now we need to create our clouds class, which is going to store all of our clouds. So self cloud images, and then we want a count for how many clouds that spawn. So self.clouds equals an empty list. That's where we will store all of our clouds. And then for I in range count, we'll want to spawn a bunch of clouds. So self.clouds, the append, and then we take the cloud object and instantiate it. And then this is where we pass in like a random position and our random image, speed, depth, everything. So this is going to get a little bit messy. We can do random.random by 99999. You might be thinking, that's way too many pixels, that's going to go way off the screen. But remember, we're looping it, so it doesn't matter how high that number is, it'll loop back to somewhere on the screen. All right, so now we can do random.random by 99999 again for the y-axis. And then we can get a random choice of our cloud image. And the next step is to get our speed, which is random.random by 0.05 plus 0.05. So that's starting with this number and going up to 0.1. So that's really slow. The idea is that, well, clouds are usually slow moving, at least in platformers. And now we can do our depth. So random.random by 0.6 plus 0.2. So we want a minimum multiplication for the camera's position to be 0.2. So that will be the camera is moving the foreground 5 times faster than the background, going all the way up to 0.6 plus 0.2, which is 0.8. So that's 25% faster for the foreground than the closest cloud. All right. So with that spawning stuff down, there's not much left to do. We can do self.clouds.sort key equals lambda x.depth. So this is a bit of some advanced code, I would say. What we're doing here is we're sorting all of our clouds here. And when you pass the key function for the sort function, it determines how you sort things, which usually you use for objects. In our case, our clouds are not naturally sortable. Python wouldn't really know what to do with them, so we have to tell it how to sort it. So what we're saying is just take the object and then sort it by its depth. So by doing that, the clouds that are closest to the camera are going to be pushed to the front for our rendering. You don't want the stuff that's moving slow in the far background to appear in front of the faster moving stuff in the front. So you got to get your layering right with this, and sort will automatically take care of that for us. All right, so just a couple more things. We need our update function for the clouds, and that's as simple as for cloud in self.clouds, cloud.update. And then we need our render function. So self surf offset 0, 0, and then for cloud in self.clouds, cloud.render surf, and you just pass the arguments along. All right, so there are our clouds. So the last step here is to import them and actually use them in the game. So we do from scripts.clouds import clouds, and then we can go over to here and say self.clouds equals cloud, and we need to pass it the self.assets clouds. So those are going to be the images for the clouds, which we need to define here. So we can do clouds load images, and this will be under data. Oh, no, not data. What is it? It's going to be data images clouds. So we're looking for just clouds, I believe, and that should load those two images as a list. And then now with our clouds here, we can go ahead and say how many we want, and then we'll just say count equals 16 for clarity. And we can go down here into our update function, and we want to make sure that our clouds render before the tiles, so we go and do that right here. So self.clouds.update, that'll just move all of them. And then we need our render function for the clouds, and we want to render onto the display and give it the offset of the camera. All right, so now if we run the game, behold, we have our clouds. And look at how they're moving slowly, which is nice. And you can see, if you look carefully, they're actually looping around, and you can tell that. And if I move fast enough, you can see that there's a bit of a parallax effect going on. So some clouds are clearly in the front, and some of them are in the back. And they all move slower than the ground in the front, which creates a really nice effect. So that's pretty much it for parallax. It's a really simple concept, but it looks really nice as well. While we may have implemented a nice tile system already, typically if you're working in some larger environments, you will want to optimize this a bit. Currently, if you look at our setup here, we render every single tile that we have onto the screen. We don't want to do that. It's much faster if we can efficiently determine which tiles should be on screen, and then only show those tiles. So one of the conveniences of the way we had our tile set up is that it's in a dictionary, which means we can look up the values. If we know where the camera is, we can calculate all the possible positions that could be on screen for the tile map. So that would be these positions right here, where we're defining them as like the string of the coordinates separated by a semicolon. So the idea is to figure out what the essentially top left tile of the screen should be, and then calculate all of those strings going down to the bottom right, and everything in between. And then we look up those locations, and if there is a tile, then we render it. So doing this, because dictionaries, if you have the key to find a value, because they have a runtime that's above 1, if you don't know what that means, that's not a huge deal, but it just means that no matter how much data you have, it's roughly the same amount of time to look up the value, which means you could have millions of tiles and still look up tiles very efficiently. So we're going to need 2 for loops here, one for the x-axis and one for the y-axis. So I'm just going to comment this out for now because we're going to replace it. So we want for x in range, and then we'll take offset 0, self.tile size, offset 0 plus surf.get width, and then divided by self.tile size, and then we'll add a +1 here. So what we're doing here is we're taking the range, so that's all the numbers in between, and then we're dividing the offset here of the camera by the tile size. So that will find what the top left tile's X position would be. Because remember, the offset here is in pixels, and our tile system is in the tile coordinates, which is just the normal coordinates divided by the tile size. And then we can take our offset 0, so same thing, and then add the display width. And by that, we find the right edge of the screen. And then we divide it by the tile size again, and that gives us the tile coordinates of the right edge. But there's an off by 1 error because of the way the coordinates work, where you need to add 1 here to get everything. So that's just adding 1 extra tile on the right side that we need to check. Alright, so now we can just do the same thing for the y-axis actually. So that would be offset 1 because that's the y-axis. And then instead of get width, it's get height. And then everything else stays the same. Now, from here, we can calculate, or actually we can change that to y, we can calculate our location string. So string x plus semicolon string y, and then we can do if location in self.tilemap, and then we can take our tile, so tile equals self.tilemap location. Alright, so now that we have our tile, we can render our tile. In fact, actually I just noticed there's a mistake here. This off-grid tile stuff is what we want to keep. It's the stuff below that we're replacing. Whoops. So I'm going to move this back up over here, and then it's this that we're replacing down here. So we want to get rid of this, and this line right here can be reused to render our tile. So we can just drop it right here, and then let's just get rid of this now. So we're using the same code where we just take the tile, so it'll take the position and the tile type and stuff to get like the image and where it should go so that we can split it. And that's all coming from the same thing because this is the equivalent of what we had before. So now that we have that, we should be able to run it and things should be the same. At least they should look the same. So yeah, you can see we have our player jumping around and everything, and the map works as expected. So you can't really see a difference here, but if you were dealing with very large worlds, you would notice a very big performance difference. And actually, even with medium worlds, if you're actually logging it, you would be able to tell. Something interesting to note, though, is that in this particular example, this is actually going to be slower than what code we had before. And that's because there's a lot of air around, and we have to look up the tile locations even if it is air. So that takes some extra calculations, whereas before we just iterated over everything. But as soon as the number of tiles, well, not necessarily as soon as, because there's a bit more overhead in doing all these calculations here, but roughly around the time when the number of tiles in the world is greater than the number of tile coordinates that would be capable of appearing on screen, that's roughly around when this will start to benefit you. And that will happen in a lot of cases. So you might think, okay, this is great, but we also have this for loop right here where we're going over every single tile. Well, this one's a bit more complicated to fix because this one, well, right now we even implemented it out as a list. There's other ways you can structure your data for this stuff to make it efficient. So if you have off-grid tiles, you're going to have to implement some extra system here to optimize the rendering. But that only needs to be done for very large worlds, because typically if you have these off-grid tiles, and remember we actually don't have any yet, but we will have them later, but if you have off-grid tiles, usually you don't have that many of them because they're usually just kind of some decorations here and there. Most of your tiles are normally going to be on the grid unless you're doing some really fancy stuff. So you can get away with a lot more when it comes to the off-grid tiles before you have to start optimizing them, which is why for this project I'm not going to optimize them. For many level-based things where you're making your levels by hand and it's not like an infinite world, you usually don't end up having to optimize your off-grid tiles. But if you do an infinite world where there's automatically generated off-grid tiles, you're going to need to implement a system for this to optimize it. And that system could be a set of quads. So you separate your off-grid tiles into quads, and then each quad will be a list of all the tiles in it. And it's sort of like the tiles we have now, except instead of mapping a tile to a location, you would map a list of off-grid tiles to that location. And then your quads would probably be bigger than your actual tile size. So you would maybe have quads that are 4 times larger in each dimension than your tiles. So that would be like 16 tiles could fit in one of those quads. But that is more of an advanced topic, and it gets even more complicated if you want to deal with stuff that's moving around, because then you have to switch which quad your off-grid tiles are stored in. But overall, it's the same principle, it's just you have to deal with all these different edge cases and handle things slightly differently. So that's something you could do in your own time if you're interested in that type of thing. Alright, so that's pretty much it for optimizing your tile map. This is one of the biggest optimizations you can do for games like this, so I thought it was important to show you how you can do it here. If you're curious about how to optimize things more in general, it's very common to see solutions to most game development related optimization problems, at least at this level. You'll see that most of them involve just using dictionaries because they have really good lookup times and you can throw as much data in there as you want. So a lot of these problems are just the issue of how can you organize your data in such a way that the basic operations that you're doing don't take as much performance. And dictionaries just end up being the solution to that most of the time, or at least part of the solution. Sometimes you're dealing with stuff like caching, where you'll want to pre-generate something and then you store it inside a dictionary so you can look it up later and then use that. But even then you're also still using dictionaries, so it's funny. Alright, so now that we have our tile system optimized, I think it's time to get into something that a lot of people would think that Pygame has supported by default, but it actually doesn't, and that is animations. This is, to me, one of the big things that differentiate something like Pygame from a game engine, is that there's no built-in animation support. If you want to animate something, you have to write your own animation system. And that's one of the things, among others, so some of the other things that differentiate it would be the fact that you have to write your own physics or your own tile system. And those are just kind of some of the basic things that people expect in game engines, although there is no formal definition for game engine. So because of all those things that I just mentioned, though, Pygame's about as far as you can get from a game engine. So we do have to keep going down this path of doing things ourselves, which is nice on some level because you get a lot more control over it. And then another way it's nice is that it gives you more experience dealing with lower level problems. In game engines, it's more like, what system that's already made can I use to solve this problem? So lots of people will have to Google very specific problems and find very specific solutions, whereas when you're working at this level, every solution is more general. So for some people, and this was the situation for me when I first got started, I actually found it much easier to make all these solutions myself than to try to figure out how to use all these pre-made things that come with engines. The other side effect is that it's a much more general problem-solving skill that you're developing by solving these types of problems. So typically, you'll find that if you're trying to do work as a software engineer, you'll get a lot better experience working on this type of level than if you were to try to use a game engine like Unity or something. And then once you have these systems already made, you can start writing your own frameworks and stuff to get to a point where you can actually work faster on certain types of projects than people using engines, which is really cool. Alright, so let's get into animations. The first thing we'll need is an actual animation class. So we need some way to represent an animation as an object. So to do that, in my utils script here, I'm going to create a animation class. So def init, this is basic stuff. So we want to take in a list of images that we want to animate. So we'll do images. And then we also want to say image duration. So this is basically how many frames we want each image in this animation to show for. And the last argument I'm going to add is loop. So loop equals true. So by default, we want our animation to loop. So let's just bind all of these parameters. So self.images equals images, self.loop equals loop, self.image duration equals, whoa, imageder, and then self.done, oops, self.done equals false. That will be set to true if you're not looping and it reaches the end, and then we have self.frame equals 0. And that will just keep track of where we are in our animation. So this is one of the most primitive types of animation setups that you can make. We're restricting ourselves to giving each frame the same duration across the animation. If we don't want to do that, we could set up a system where each frame has an assigned duration. You go and do all the math and try to figure out when to move to the next frame and stuff like that. And you can add all sorts of other rules to your animation. If you actually look at some of my games, you can find the animation code and it gets a lot more complicated than this. But this is a very simple one. So the idea is to just take all of your images and then just render your images based on your frame, and then that frame increases over time. And then we also loop it. And that's enough to get us a nice animation. All right. So one of the first things we'll want to do here is we want to be able to copy our animation because if you notice, we're taking in our images and we have all of these, or specifically these two values that are specific to an individual animation. So the way I'm going to set this up, and this is, some people might say this is bad code, some people might say it's good code. For this use case, I think it's pretty good because it's a simple solution. But the way this is going to work is that we create an animation for each animation in the files, and then we have it somewhere that's easy to reach. And then every time something wants to use that animation, it will copy its own instance of the animation. So something important to note is that the way Python works is that if you have a list and you assign something else to that same list, or even an object, it's just any object in general that's not like a primitive value, it will be a reference to it instead of actually copying it. So let me demonstrate here. Let's do def copy self, return animation. So that's just making another one of itself. And we pass it self.images, self.image durations, or duration, self.loop. So I'm passing in the images that it already has, the same duration in the loop. So it's all the same values, so it'll generate pretty much an exact copy of itself. But like I was saying, because we're passing in images here, it's not actually making a copy of the images. You're just getting the images, the same list of images. So if you modify it in one of them, it will affect both. So that's something to be careful about, but in our case, that's actually to our benefit because we can copy this as much as we want. And then all those images don't take extra memory because they're all looking at the same thing. All right, so with that copy done, we now need a way to render our animation. So let's do def image self, and instead of actually rendering it to a surface and like having a render function, I'm just going to make it so that you can get the current image of the animation, because that's a little bit more flexible because we can use that image however we like instead of being in a situation where we have to give it a surface to render to. So for this function, we'll just return self.images and we'll do int self.frame divided by self.image duration. So we're dividing our frame by how long each image is supposed to show for. So frame here could, I guess, be interpreted to mean a couple different things. So it could be frame of the animation, or it could be frame of the game. So in this situation, we're going to be using it as frame of the game. I think in some of my projects, I use it the other way around. But in this case, we'll increment our frame value every single frame of the game. And then every single time it crosses this threshold here, this whole value, since it's truncated to an integer, will go up by 1. And that will be the index used to select which image we show. So this will just give us whatever image we should have for the frame that we are on. Now we can do def update self, and we need to actually increment our frame here. So if self.loop, we want to do it differently if we have a loop versus if we don't. So this is not as simple as self.frame plus equals 1, because you'll run into a problem where let's say our frame goes past the end of the animation. You'll get an index error on our images list because you're trying to access an image past the end of the animation. So we have to make sure that this loops properly, and then also for if the loop is not enabled, it needs to stop at the end. So here's how this is going to work. We'll do self.frame plus 1, so that's the same thing as plus equals 1, but we want to add an extra step here in this calculation. So we're going to do modulo, so that's the remainder of self.image duration by len self.images. So this will force our frame to loop around once it reaches the end. Because remember, I mentioned before that pretty much anytime you want to loop anything, usually you're going to end up using a modulo, because the remainder is effectively creating a loop. Alright, so like I said, it goes to whatever the maximum frame is for animation, which is calculated here, and then it just loops around. And then we'll also want to do, if we don't have a loop, so that'll be else, and we do self.frame equals min self.frame plus 1. That's the same plus 1 thing, but we have a min here this time. So we don't want it to go past the end of the animation. So min takes in 2 values and then returns the lower of the 2. So that'll be that we define what our end of animation is right here, and if for some reason this value is greater, it will return whatever the end is. So self.image duration, and we did this before, by len self.images. Now the one thing we have to be careful about is just being off by 1, because technically, let's think about it like this. So let's say you have an image duration of 1 and you have 3 images. So you say, okay, our last image is number 3, and this math will give us a maximum value of number 3. But lists are indexed starting from 0. So the index 3 does not exist. Because of that, you have to do -1. And you might be thinking, well, wait, we didn't have to do that up here. And that's because of how modulo works. If you take the remainder of, let's say, 3 divided by 3, you get 0. So if our end here, let's say our last frame is frame 3 for some reason, then it'll go 0, 1, 2, and then loop back to 0, because you can't have a remainder that's equal to whatever you're dividing by. So remainders actually naturally deal with that issue. We just have to account for it here because this is a different system. All right. And actually, if you're curious about why arrays start at 0, that's actually one of the reasons why it's convenient, at least in game development. There's a whole load of reasons why it's better for them to start at 0, but this is one of the ones where it's convenient, is just being able to do this here. All right, so we do if self.frame is greater than or equal to self.image duration by len self.images -1. So this is just doing that comparison with this value right here. And you could do is equal to. I don't like to do that because this is a broader condition. If we made a mistake and maybe we went back and changed this for some reason, this will not just suddenly break because of that. So I prefer to, when possible, just do the broader condition, if it makes sense. So yeah, we're just saying if the frame is greater than this, we can do self.done equals true. Although technically if it's greater, we'll get an index error down here, but just to be safe. So this will set done to true when it's actually done, and the frame can't go past the end, which is just what we want. All right, so we have our animation class. So now we need to be able to load our animation. So for that, we go over to game, and we need to find our animations. So if you go over here into data, we have images, we have entities, we have player. This is a lot of files. But then here we have all of our player animations. We have like idle. And then this is like 21 images. We've got jump, which is a single frame. So you might think of an animation as multiple images, but in this case, we're going to generalize it so that the player is described as having a state that is an animation. So even if when we're jumping we don't want to show multiple frames, we just load the animation of that one frame that we want to show, and we say, okay, we're on this animation, and that's how we'll implement that later. So we also have run, 7 frames, slide, 0 frames, wall slide, 0, well, it's actually 1 frame, not 0. But we have all those animations, we need to load them in. So you could write something fancy to load all these in automatically, but for this, it's easier, well, quicker, just for the scope. If you're creating a bigger game, I would actually write something to load this better, but for this tutorial, I'm going to do it by hand, so we'll do player/idle equals, and then we'll actually have to go up here, and in utils, we'll want animation. We'll do animation of load images. Remember, the first parameter for animation is the set of images we want an animation of, so we can just pass in what images we're loading here. We can do entities slash player slash idle, and then we'll set our image duration to 6, because I mean it's an idle animation. We want the animation to probably go a little bit slower, because it's just kind of that the player is inactive and just kind of bouncing around or whatever. All right, so we have our idle animation. Now we need our run animation, and then this is just the same thing. You grab this, swap all those, and then I'm going to set the image duration to 4 because it's a running animation, so you're running, it makes sense for it to cycle a bit faster. A lot of this depends on how you actually drew everything. This is not a hard rule, it's just a number that makes sense for whatever your assets are, and in my case these are the numbers that make sense. You can play around with it if you don't like the durations. For all the remaining ones, I'll use the default of 5, because most of these don't even have multiple frames. So we have jump, slide, and wall slide. All right, so we should have our animations loaded here. We can do print self.assets, and we can see what we have. All right, so if we look down here, here's our stuff here, and you look, we have like player jump, and here's our animation object, and run and idle and stuff. And now the last step here is to actually use these animations to render something. So for that, we need to go over to our entities here, and we need to add a few new things. So we'll do self.action equals a blank string, self.anim offset equals, and then this is going to be a bit of a hack in animations, because say the object that you're animating will have varying dimensions. Usually the way you do this is you add padding to the edges of your images so that you have space to animate the changing sizes of your whatever object you're animating. So for example, if I go over here and I go entities, player, run, let's look at 0. It's hard to see here. Right here, look at, there's all the space to the sides. And then if you look at, I don't know, maybe, oh, here's a good one. See, look, now this foot's sticking out a lot, so we need some of that space on the side. But if you remember, this player image does not have that padding. And if you actually go back to, let me close all this. If you go back, where is it, to our game here, our player's dimensions are smaller than those images we have. So a trick you can use is to render your images with an offset to account for that padding, so that our animations overflow outside of what would normally be the hitbox for the player. Normally you would have changed this offset for each entity. In our case, I think just setting it to -3 should cover everything. This is the value that the player needs. We can inherit from this and override it later if we wanted to use something different. But this is just the number that we're adding to wherever we intend to render the image, which will just offset where it's going to be rendered. All right. So we also want self.flip, and that's because the player should be able to look right or look left. We only have our animations facing in one direction, so we need to be able to just flip our images, which I'll show you later. Self.setAction idle. So this is the function we're going to have to do right here. We need to be able to set which animation we're currently using. So to do that, we need to create our function here, and we'll call it defsetAction. Self action, and these are just the string names of our actions. So if you remember, the player has the idle, run, slide, wall slide, jump animations. So it's just the string of those names, and then it will find the animation for that. So if action does not equal self.action, so we only want to do this if the action has changed from what we already have saved. Self.action equals action, so that's just updating it, and then we update our animation here. Equals self.assets self.etype, so that's the type of the entity. So it'll look for player slash, and then self.action, so it'll look for player slash run, for example. And then we want to copy that. That's, remember, our animations up here are in our assets, and they're these animation objects which we had the copy function for. We're just calling that copy function, which is creating a new instance of that animation. And this is why we need this case here, to prevent it from being called if you set the action multiple times, because it's more convenient. I have found to be able to just say this is the current action each frame, than to specifically determine when it should be changing. And then what we do in here is just say, check if it has actually changed because of this function call, or if it should change because of this function call. And if what we're setting it to is different from what we had, then that's when we want to grab the new animation, because the way it's going to work is we're going to say every single frame while we're running, we're going to say set action run. And if this were called every single frame, then if you remember over back here, we set frame equal to 0, and this will happen whenever you copy it as well. So it would be permanently stuck at the 0th frame. So this animation can only be created when you switch to the animation. All right, so now we need to be able to actually render our animation. So we go down to the render function here. And remember, we had this hack here where we just use the player. We don't want to use that anymore. So what we'll do instead, I'll comment this out for now, we'll do surf.blit, pygame.transform.flip, self.animation.image, self.flip, false. So this is just handling the flip part. So we have the flip attribute here that we created up here. We'll be updating this in the update function. And then we're using pygame.transform.flip. So this is just, first of all, taking the output of whatever animation we have. This is where we actually get the current frame of our animation. And this is why I mentioned that I think it's better in our use case to just take the image of the animation rather than creating a render function. And that's because we might want to do something like this, where we flip our image before we render it. So we flip our image, and this is the x-axis flip, and this is the y-axis flip. So we don't want to like flip it top over bottom. That there's no use for that in platformers for the most part. Like for entities, usually it's like facing right or facing left. You don't face up and down. Some entities you might do that, but for most of them this will be sufficient. All right, so this function here will output the flipped image that's appropriate, and then we can work on our position here. So for our rendering position, we'll do self.position 0 minus offset 0. So that's the camera offset. But then we also have that other offset, which is the animation offset. So self.anim offset 0. And then we do the same thing for the y-axis, which is self.position 1 minus offset 1 plus self.animation offset 1. So that's a bit of a long line, but there's all these different offsets to account for. But they mean different things and they have different uses, which is important. All right, so let's go ahead and delete this line. And that's our new render function there. The next thing is we'll need to be able to update our animation, and that's simple. We just go over here, and this is the update function right here. We do self.animation.update. All right, there's just one more step that we could do right here in this object, and that will be the flip. So we'll do if movement 0 is greater than 0, self.flip equals false. If movement 0 is less than 0, self.flip equals true. So if you remember, our assets are facing right. It would be the inverse if they were facing the other way around, where our assets are facing right. So if you're moving right, which is what this case is, we set flip to false because we don't want to flip our image because it's already facing right. But if you're facing left, or well, you're moving left, our images are facing right, so we have to flip it, and that's why we say flip equals true. All right, so that should be everything for this class here. I'm actually going to create a new one, and this is where we get into a bit of the fancier stuff. We're going to create a player class. So we do class player, and we will inherit from the physics entity. And we'll do def init self, and I'll take a reference to the assets because it'll need that. Position, size, and we'll do super.init. So this is just calling the init function from the physics entity. Actually, wait, we don't want to reference to the assets. We need a reference to the game. And also the mistake over here that I made. And the reason this is happening is because in my reference code, I didn't do the full object-oriented stuff the same way I'm doing it here, but that's not super important. Anyways, so the mistake here is this needs to be self.game.assets. So we're here, this is .assets. All right, so anytime there's .assets, actually that's the only one, so that should fix it. But yeah, so we pass in to the initialization function for the physics entity. We pass in game, position, size, actually, and there's one extra thing. It's game, position, size, but then we have our entity type. And because we're dealing with our player here, we know that the type is going to be player. And actually, wait, I know another mistake here. So that should be self.type. But anyways, so we're passing in our type that's used here to look up our animations, and we know that that's going to be the player for our player. So we just pass it in here. We don't have to put it in as an argument there. We could if we wanted, and there are use cases for that, but this is fine for now. So now we need an update function for our player. Self tile map movement equals 0, 0. And we want to use the default update function tile map movement equals movement. And then this is where we get into some of the magic. So we want an extra attribute for our player here. We'll do self.air time equals 0, and this will just keep track of how long we've been in the air. So self.air time plus equals 1. And the objective here, the reason why we're inheriting and adding our own code here is because each entity, well, not necessarily each entity, but different types of entities will have different animation logic. So we're writing the animation logic for our player. And that's why we separate it with inheritance here. All right, so we do if self.collisions down self.air time equals 0. And then if self.air time is greater than 4, we'll do self.set action jump. So if you're in the air for a while, you want to show the jump animation. All right. And then elif movement 0 does not equal 0, self.set action run. So if the x-axis of our movement is not equal to 0, that means we're moving horizontally, which means we're running. So, but if you think about it, if you're in the air, you probably want to override the run because you don't want the player to be showing an animation of running in the air. You probably want to override run with jump. That needs to be higher priority. So by doing if and then elif here, we're saying this one right here is the highest priority. And then if this is not the case, then we can move on to this one and say, okay, are we running? And then if not, if we're not jumping and we're not running, we're probably idle. Self.set action idle. All right, so we have 3 animations. Those other ones are for extra things. We'll get to that later. But we have our 3 animations implemented. So the last step here is to actually use our player class. So we're going to go over to game here, and we're going to take from our entities and go player. And when we create a player, we want to do player and remove that. And now we're instantiating a player, which is inheriting from the physics entity instead. All right, so if we run our game now, I still have that print statement. So you can see there's an idle animation of me just standing there. And if I run around, you can see there's a running animation. If I jump, you get the jumping animation or the jumping frame. So that's how you do animation. It's a pretty simple concept, but there's a lot of random stages to the implementation. Animation is all about just showing different images at different times, so it's fundamentally not that complicated. It's just that it's nice to have different levels of abstraction that make things easier to work with. Because in the future, if you want to add another entity, you pretty much just have to load in the assets and you say, well, create another object like this, and then you write the custom logic right here and you're done. And also I forgot the extra thing I didn't really point out was that you can face right, you can face left, and that's based on where you're moving, which is nice. All right, let me just remove this last print statement here. And we're done with animations. Woohoo. With our animations done and our tile system optimized, you might be thinking that our world here is looking a little bit empty with these 2, I guess, slabs or whatever of tiles. So it's time that we start to fill out our world. But placing tiles by hand or by just coding up the individual tile placements is pretty tedious. So oftentimes it's a lot better to use a level editor. For some games you'll write a map generator or something like that, so that it's all dynamically generated, but for most games you're going to need to touch a level editor at some point. There are plenty of good level editors out there, but a lot of them are lacking in flexibility in certain areas, so I prefer to write my own. And additionally, there's a lot of random things that are going to come up if we do write our own editor, which we will be, that are unique topics in themselves that are useful to know about. So for example, by default, this game I'm working on won't have any mouse input, so working on a level editor will make it so that you can learn about that here in this tutorial. So when you think about a new, project, one of the important things to think about are inputs and outputs. So in a level editor, you're inputting your keyboard and mouse input to create a level, and then the output is some sort of file that represents your map. It's also worth noting that if you want to be able to edit a previously made map, you also need to be able to load that map back in. So that means that one of the core features that our level editor is going to be dependent on is the ability to be able to save and load map files. So you might be wondering, how do we save our maps? One primitive technique, which I think I alluded to earlier, is to just have a grid of numbers, for example, where you could just do 0 for air and 1 for ground or something like that. That's pretty much the most primitive you can get. What we'll be using is something called JSON. It's a file format for storing objects that basically fit into the format for how Python stores dictionaries and lists and values and strings and stuff like that. So it can't store things like objects or classes, but if we encode it into things it can understand, and that's like the dictionaries, lists, and stuff like that, then we're able to store it and then load it back in. So one of the major differences between Python's dictionaries and lists and JSON is that JSON has no support for tuples, and all of the keys for dictionaries must be strings. And if you remember back here, I think I mentioned that, for example, for this location thing, it would have been easier if we could have just taken the tuple of X and Y, because you can actually use that as a key for a dictionary. But for saving files, you can't have that as your key because it will be interpreted as a list, and then that can't be easily converted into a string, and then you run all sorts of other problems. So we have to sort like a string like this. In higher level use cases, so what I actually use is I created my own function for saving and loading stuff like this, where it's built on JSON, but then I added support for tuples. That's a bit of an extreme case, but that's a direction you could take this in if you wanted to do that. Anyway, so for what we'll be using here, this format's fine, just the string, semicolon, string. If you're wondering where JSON comes from, JSON actually stands for JavaScript Object Notation. It was originally made for JavaScript and dealing with JavaScript objects, so it's naturally meant to represent objects, so it works well with tile maps. If you work with actual level editors, you'll find that you can actually export to JSON usually. Either that or it will have its own custom file type. And by the way, while I will be making a level editor to show you some useful features with Pygame, don't feel like you have to be using your own level editor. After this tutorial, you could go out and get a normal level editor, and then you can just write a way to interpret that into a tile map. So you would take this tile map object here, and you'd probably have like a load function. You take whatever that level editor is outputting, and you figure out how to convert it into what you need. Or you can build your tile map system around whatever the level editor provides. But in my case, I can make things work very nicely if I just write my own. So to get started with our level editor, we'll probably want to make another script here, and I'm just going to go new file, and I'll call it editor.py. And then I can go over to game. I'm just going to copy this whole thing, and then I can go back to editor, paste this in. Instead of calling it game, I'm going to call it editor. I'll go down here, call this editor, and then let's trim down what we're actually using here. So we won't need load image. We will need load images, and we will need a tile map, but we won't need like players or entities because this is for tiles. We don't need the clouds, obviously. And then let's add a constant here called render scale, which will determine just how much we're multiplying the size of each pixel. So let's change the name here to editor, and then let's go over here and let's trim down all these assets. We don't need most of these. We just need the ones we're making our world with. So for this here, I'm going to take this movement thing, and we will be using this surprisingly because you'll want to be able to move your camera around. So we'll do false, false, false. Instead of moving right and left, you're going to be able to move the whole camera instead of a player in all 4 directions. That's why we need 4 values here. All right, so let's remove some of this stuff. We do need our tile map, in fact, because we're making a level editor, so we can keep that. We'll also want to keep the scroll because, well, we're going to be having a camera that we move around still, so we need to keep that. And let's go and trim down this stuff over here. So we don't need a whole lot here. We can just delete all that and change the background to black. And then there's a couple things right here we can use. So let's remove these, and let's say if event.key is pygame.kup, self.movement2 equals true. And then we can go over here and say k down and say movement 3 equals true. So now we can copy all this, go over here, paste, and then switch these trues to falses. And then this will automatically update our movement thing here, so we can start moving around with that. But we don't have anything to see yet, so there's nothing here. So let's just run this real quick and make sure that it works. Oh, we actually don't. This is not supposed to be bullet, that's supposed to be fill. Alright, so we have our editor. It's just completely blank though, because, well, we don't have anything to show yet. So the first thing we're going to need is the ability to select our tiles. So normally I would create an interface where you can click the tile you want to use, but because I'm trying to keep this simple, I'm going to make it so you just press buttons to change which ones you're using. So let's say self.tilelist equals list assets. So, or self.assets. This will convert our assets into just a list of these values, because if you run list on a dictionary, it just gives you the keys. So it's giving me decor, grass, large decor, stone, etc. So that'll give us the 4 values there. And then let's do tile group, or self.tilegroup equals 0, self.tilevariant equals 0. So with these 2 variables here, we'll be saying which group are we using. So we're using grass, decor, etc. And then the tile variant will be which tile in that group are we using. So we'll have different buttons for changing between the group and the variants, and that way we can rotate through our different tiles in a more efficient manner. Alright, so let's go ahead and write something for showing which tile we have selected. So in our for loop here, we will need to calculate what our current tile is. So let's do current tile image equals self.assets. We'll do self.tilelist, self.tilegroup. So this is going to be one of the more messy indexing situations again. And then self.tilevariant. And we'll want to copy it because we'll want to show it with an alpha. So current tile image.set alpha 100. So what that'll do is it'll set it so that this image is partially transparent. If you set it to 0, it will be fully transparent. If you set it to 255, it'll be fully opaque. So we want it to be a fair bit transparent because we want to be able to see what's behind it. This is supposed to just be a HUD thing so we can see what we're doing. So we can do self.display.blit, and then we'll say current tile image, and then we'll put it at 5.5. All right, so if we run the editor now, you can see that we have a tile up here. So that's just our grass decor, because coincidentally, decor is the first value of our dictionary here. So with that, we can now see which tile we have selected. And if you're confused about this right here, you can kind of just dissect it. You can print out the different stages of it. So you can like take this part here, you can print that out. You can take this part, you can print it out, and you can take this whole thing and print it out and see what's going on. But what we're doing is we're taking from our list of tiles, we're using the index that is our group. So this will be an integer that represents the index. And then we're selecting from our assets that group, and then we're grabbing this tile variant, which is another index. All right, so now we need to be able to switch which tile we have selected. And this is where I'm going to introduce something new. So we have if event.type is pygame.mouse button down, if event.button is 1, clicking equals true. So we're doing a couple of new things here. So first of all, mouse button down, that's a new event type. So remember, we've been using key down and key up. Mouse button down is when you press down on a mouse button. So, or it's not necessarily that, because it's more like when you activate a mouse button, because it also can trigger on your scroll wheel, which we'll get to later. Actually, wait, sorry, for this clicking thing, we'll need self.clicking equals true, and then, or false rather. And then we'll put it to true here, there we go. But, so mouse button 1, that's your left click. So we'll set clicking to true there. Now you might be thinking, well, if left click is mouse button 1, is right click mouse button 2? In fact, it's not. You're looking for 3. and we'll set self.right-clicking equals true. And then I'll throw that up here. We can go false. All right, so if right-clicking is 3, what is 2? Well, you could look up in the Pygame documentation to see, but for 2, it's actually when you press down on your mouse wheel. So there's a couple more that we're actually going to be using here. We need to be using 4 and 5, and 4 is when you scroll your mouse wheel up, and 5 is down. I think it might be the other way around. I always get this mixed up, but I think 4 is up. So let's do if event.button is 4. Let's say tile variant, self.tile variant. Actually, let's do group here. Tile group equals self.tile group -1, and this is using that modulo trick I was talking about earlier, where you can get something to loop by using modulo, and we're going to subtract our tile group here, and we'll be modding it by length of tile list, or self.tile list. So when you reach the end of that list, it'll just loop around to 0. And then if you go less than 0, it'll go to the end of the list. So that's convenient. That way we're forcing our index to be in the bounds of what groups we can even select. So now we can take this and then also go do 5, which I believe is scrolling down. So we do +1 to scroll down, and then mod it by the same amount, and that will also loop. So now we can select which tile group we're using by using our mouse buttons here. So if I run the editor and I scroll up, you can see the tiles are changing on the top left. So these are our different groups. So we have our grass, our decor, our stone, and our other decor. So we can now scroll between groups, but we need to add something so we can scroll between variants. So to do that, let's go ahead and add self.shift. I'm going to use kind of a key combination for this, and I'll say if event.key is KL shift. Note that I'm not doing right shift here. Shift equals true. You could add right shift too if you wanted, but I'm not worrying about that right now. So now this shift variable will toggle based on whether or not we're pressing shift. So what we can do over here is we can say if shift or self.shift, we do this. Otherwise, we do that. And then what we can do here is we can swap the tile group with the variant. So we say tile variant. So if you're pressing shift, we will scroll through the variant. And if we're pressing or not pressing shift, it'll scroll through the group. So we do this. But the one thing we do have to change here is that the thing we're modding by can't be the tile list again. It needs to be the number of variants that we have instead of the number of groups that we have. So to get that, it's kind of based on this thing up here. So we just do the length of self.assets, self.tile list, self.tile group. And then that will give us the number of variants. All right, so we can take these, and if we run it again, I can scroll as I did before and go through the different variants. But if I go to, like, say grass here and I press shift and start scrolling down, you'll see all the, or sorry, this scrolling without shift goes to the different groups. And then if I press shift, it'll go through the different variants within the group. Something I just noticed I forgot though, is that you want to make sure that if you change the group, you set the variant to 0. Otherwise you could run into some index errors. So we'll want to do 0 here. And it makes sense. If you change which group you're looking at, it makes sense to go to the first item in that group. So if I go to grass here, go to like a variant down here, and then I go to the next thing, it'll go to the very first variant of that group. All right, so we now have our tile selection working. So now's the fun part. We need to be able to place stuff. So if you notice, I already wrote some stuff for clicking. We do need to do a couple things to finish this off. We need if event.type is pygame.mouse button up. And we can do if event.button is 1, self.clicking equals false. If event.button is 3, self.right clicking equals false. So now these clicking variables will be updated based on whatever our mouse state is. So let's go over here. And this is where we need to start rendering our tiles and doing all of that magic. So let's start by rendering our tile map, which we can do right over here. We can say self.tilemap.render, self.display, and then we can give it our offset, which We need to set up this render scroll thing again. If you remember, we need to convert our scroll here into an integer thing. So we can do render scroll equals the int of scroll or self.scroll 0, and then int self.scroll 1. All right. So we have this render scroll thing, which is the truncated version of our scroll. We throw it in as our offset there, and our tile map can render. We can run this, and actually, in fact, I forgot about something. We have this code right here that automatically populates our tile map, which is fine. So we can see that there is something there now. But we want to be able to place tiles. So to do that, let's go down to here, and let's say mouse position equals pygame.mouse.getPosition. So this is a new thing as well. So this will give you the pixel coordinates of your mouse with respect to the window. So if your mouse is in the top left of the window, it'll give you 0, 0. So what you can do with this is you can use this to figure out where your tiles should go when you're clicking. Something you do need to be careful about is that we're actually scaling our image up here so that our pixels are actually 2 pixels now. So we actually have to scale down our mouse position to get the correct coordinates. So we can do m position equals m position 0 divided by render scale. And that's why I wrote this constant beforehand. And then we do m position 1 divided by render scale. So that's what that constant up here is for. That's so that we can divide right here and get the correct mouse coordinates. All right. So with that, we can say tile position equals, so this is going to be what our mouse's position is in terms of the tile coordinates. So we've done this before, but with other things. So we'll want to say int of the mouse position plus the scroll, and then we can divide by the tile map size. And then, actually these need to be self again. Then we can do mouse position 1 plus self.scroll 1 divided by self.tilemap.tile size. And that will give us the coordinates of our mouse in terms of the tile system. So with this, we can say if self.clicking self.tilemap.tilemap, and then this is where we're assigning our new tile here. We can go string of tile position 0 plus, and this is the weird string thing we have to do, tile position 1 equals type, and we'll want to say self.tilelist and then self.tilegroup. So this is converting our index selection into the string name for the group. And then we need to take our variant, which will be the self.tile variant. Fortunately for us, this one is just an integer, the way that we store our tiles, so that makes things easier. And then for the position, we can do the tile position. All right. So with that, we should be able to place tiles now. So here I've got my grass decor thing, and if I switch over to actual grass, then I can place that by left clicking, and I can place rocks and stone, and I can change the variance. So that's all nice and all, but we need to be able to delete tiles as well. So for that, we can do if self.right clicking, we'll do tile location equals, and this is just a string lookup, so don't confuse it with this. I use position and location interchangeably, but they do mean separate things here. Not because of the name of the variables, but I'm using them for something different. So we do tile position 0, and then string tile position 1, if tile location in tilemap.tilemap, or self.tilemap.tilemap. That means that this location that we're hovering exists, or the place that we're right-clicking exists. And if it does exist, then we can do del self.tilemap tile location. So with that, I can run the editor, and I can, oh, it crashes. And I need one more tile map there, because we need the tile map attribute of the tile map object. So now if I right-click, we can delete all these tiles that are already there. And while we're at it, since we can now place tiles, let's go ahead and remove this code here that adds in tiles by default. All right, so with that removed, we can go back to our editor here, and if we run it, our pre-placed tiles are no longer there. So there's a couple extra things we need to be able to do. So first of all, it would be nice if we could see kind of roughly where the next tile would be placed. So to do that, we can say right here, self.display.blit, and then we'll do current tile image. And we want to show it at the tile position 0 by tile map.tile size, or self again, minus self.scroll 0, self.tile position 1 by self.tile map.tile size minus self.scroll 1. All right, so what that's doing is it's taking the, or actually that doesn't need to be self. It's taking the tile position we just calculated here, and then converting it back into pixel coordinates by multiplying it by the tile size. And then we're adjusting that position based on the camera for rendering. Because if you remember, we added scroll right here, so we need to remove it right here because we're going to show an overlay of where the next tile is going to go. All right, so if you're confused about why we're going through all this extra effort instead of using the mouse position to show this indicator, it's because we want it to be aligned to the grid. And the part that does the aligning is right here on this division. That will force it to be aligned, and then we scale it back up into pixels, and then it will be snapped to the grid, which is convenient. All right, so with this, if we run this, we can see where our next tile is going, which is very nice. So if I go right here, I can go down into a tree, and you can see, look at that, I can see where my trees are going before I even place them. So now we did all the stuff with scroll, but it would be nice if we could move our camera. So to do that, we just used some of the simple tricks we had before. We can say self.scroll 0 plus equals self.movement 1 minus self.movement 0, and we'll multiply by 2 just to make it move faster. And then we'll do 3 and 2 for here for the y-axis. If you remember, this is if you're holding down right, minus if you're holding down left, and this is down and up. So all of this adds up to figure out how much you should be moving your camera by here. And then we just multiply it by 2. So that will move our camera based on our keyboard input here. So if I do, you can actually see it without me even placing anything because the grid's moving around. I can move around and things are moving, which is nice. So if I draw these things, I can move around and look at things, which is convenient. All right, so the next thing I'll want to do here is probably, it would be nice if instead of using these, we could use WSD because we're drawing with our mouse. So let's do KA because that's left, KD, KW, KS. And then we'll have KA again, KD, KW, KS. So now we can move around with WASD, which is much nicer. All right, so now that we can move our camera around and we can place tiles, the next thing is to be able to place things that are not on the grid. Because if you remember from the beginning of the tutorial, from what I showed you for what we're making, there were a lot of tiles that were not on the grid. And we did all that code that I mentioned that we weren't using quite yet for rendering tiles that aren't on the grid. So let's add a variable here. Let's call it self.onGrid equals true. And then let's go over to here and let's say if event.key is pygame.kg, and then that will be not self.onGrid. So what we're doing here is we're making it so that this variable here represents whether or not we want to be drawing tiles on the grid or not. And then if you press G, it'll switch it. So if you just set something or a boolean to the not of itself, that just flips it, whatever it is. So we can now start writing some rules for how things will be placed depending on whether or not we're on the grid. So the first thing we got to do is update our indicator, because our indicator assumes we're snapping to the grid, which only happens if you're rendering on the grid. So if self.onGrid, we do this. But if we're not on the grid, we do, and this is the simpler version that you might have thought of at first, self.display.blit, and then we take the current tile image and we just throw in the mouse position, and then we don't have to do all of this crazy math to figure out what the snap grid position should be. All right, so if we run this now, I could just play some stuff, and then let's pull out the tree, I guess. So you can see the tree snapping around. If I press G, it becomes smooth. But it's still placing on the grid. We need to make it so that we can place off the grid. So for that, we need to modify this code right here. So we do if clicking, and in fact, we need to do if clicking and self.onGrid, we do this. Now, we don't want to place a tile every single frame off grid just because we're clicking, because there's no grid value that we're overwriting. Instead, it would just place 64 tiles per second, or not 64, 60 tiles per second because we're running at 60 FPS down here. So we don't want that. We want it to be, because off-grid stuff is not snapped to anything and we're not overriding anything, we want it to be able to just place a tile when we click and just press down that button. We don't want it to be placing non-stop. So you would click for each tile you want to place. It's just the easier way to do things. So for that, we don't need an extra variable or something to keep track of that input. We can just go right in here to the clicking thing for mouse down on 1, and we can write it here for placing. So we can say if not self.onGrid, we can say self.tilemap.offGrid tiles, and that's that list we had before, the append, and we'll say type is tile list, and this is pretty much the same stuff from before. So self.tilelist, self.tilegroup, and then we want the variant, which we know is just the self.tile variant. And then the position will be just the mouse position 0 plus the scroll self.scroll 0, mouse position 1 plus self.scroll 1. And if you're wondering why we're adding the scroll to our mouse here, and we did a similar thing with placing stuff on the grid as well, the reason is that from the camera's perspective, the top left is 0, 0. But in the world's perspective, let's say that your camera's 100 pixels to the right, and you place it at the coordinate 0, 0 in your window. Well, the coordinates in the world for what 0, 0 on your window is becomes whatever the coordinates for the camera were. So we actually have to add the coordinates of the camera to convert from the display space, so where you're clicking on the window, back into the world space. So if you remember from the tile rendering, it's actually the other way around, where you have to convert the world space into window space by subtracting the scroll. So it's just doing the same thing and you're just flipping it. So we should now be able to place our tiles that are off grid. So if I press G, I can left click and I can place stuff that's not on the grid. So if I draw these right here, you can see those flowers were not aligned, which is nice. But now we can remove all of those flowers that are on the grid, but we can't remove the ones that are off the grid. So we need to be able to add that too. And for that, this is where things get a little bit messy. This is the unoptimized way to do it, but for level editor, it's probably not going to be a huge issue. If you're lagging a little bit when you're using your level editor, it's not a huge deal. You should be more concerned if your player's lagging from playing the game. So we can do some bad code in here. So we'll say for a tile in self.tilemap.offGridTiles.copy. And the reason we're copying here is because we're going to delete if this tile is touching our mouse. So we don't want to mess up our iteration. So we just take a copy of the list so that we don't get the reference. So we can calculate our image. For our tile here, we can do tile image equals assets self.tile type tile variant. So this is like when we were rendering the tiles. So we need this image to be able to compute what the bounding box or the hitbox of this off-grid tile should be, because the trees are a lot bigger than the normal tiles. So we want to take the image to figure out how big of a hitbox it should have for deletion. So we can now calculate that hitbox. We can do tile r equals pygame.rect, and we'll say tile position 0 minus scroll or self.scroll 0. And remember, this is because we're converting our tile or world space into display space because we're about to try to collide it with the mouse. So we can do tile position 1, and you could actually do this the other way around, where instead of subtracting the scroll here, you could actually add it to the mouse's position to do these collisions, but we can do it either way, and I'm just choosing to do it this way. So we'll get the width of our image, and that will be the width of our rectangle here, tile image.get height, and we can do it for the height. And now we have all of our 4 parameters for our rect, and we can do if tile r.collide point. I don't believe I've shown you this yet. So with rects, you can collide with other rects, or you can collide with a point. So instead of passing in a rect now, we could just pass in a point and it'll tell us if it's colliding. So in this case, we'll just throw in our mouse position and say, is this tile colliding with our mouse? And we can say if it is, well, we can do self.tilemap.tile, or actually no, off-grid tiles.remove, and then we want to remove this current tile. So with that, we should be able to remove our off-grid tiles now. So here's some on-grid ones, and then let's place some off-grid ones. So let's do that. So we can remove the on-grid ones and the off-grid ones now, which is nice. So that's pretty much the basic functionality for a level editor. The next step is the thing I was talking about at the beginning, and that's the loading and saving part. So for this, we'll actually have to go back to our tile map code here, and we have to add some new functions. So we need a load function and a save function. Let's do save first, because you can't load anything until we've actually saved something that we can load. So let's do save. We'll take self, and we'll take a path to save to. And then we just do f equals open path w. So this is just normal file handling in Python if you haven't done it before. I'm going to import a new library up here. We're going to do import JSON. So this is the format I was talking about before. So fortunately in Python, there's a module that makes this really easy to work with. So all we have to do, and this is super simple, json.dump, and then we want to throw in a couple things. So we'll say the tile map, and this is like a dictionary, remember? So we need to split up our information here. So we have a tile map, which is all this tile data on the grid. So we'll do self.tilemap, and then we'll do tile size, which is the size of the grid, and then off grid. So this is all the off grid tiles. So self.offGrid tiles. And then this dump function, as you can actually see here, VS Code is telling me, it takes the object we want to dump and then the file pointer. So that will be just F. So we told Python open this file, and then we're telling it to dump this object right here into this file, and it will convert it into JSON for us. Now if we do f.close, it'll save it. So if I go over to my editor here and let's say create a new key binding, let's do event.key is pygame.k, and I really like to use O for this because I think O is output. We are already using S for moving the camera down, and I don't want to do like Control S because then I have to go add the control key. So I like O. It's also far off to the right, so you're not going to accidentally press it. So self.tilemap.save, and let's just call it map.json. Remember, the parameter we give it is the path that we're saving to. So now if I run the editor, and let's just place a basic setup here. So let's just place some tiles, do this. So we've placed some tiles. And let's do some off-grid ones too. So let's find our tree, and we'll place it off-grid. Look at that. We got some trees. And then we can go and place some of this, these flowers here. So if I press O, you can see over here on the left that I had a file pop up. And this is the file we just saved. So this is kind of hard to read like this. I actually don't know how to turn on the wrapping on VS Code. Presumably there is a way to make this wrap, but we have all of this data here. So we have tile map, remember that's where we dumped all our tiles, and you can see this is the key, this is the type, the grass, variant, position, or variant position, and it just looks like it's just a Python dictionary and list, like I was mentioning. So it's almost one-to-one. Like I said, it gets rid of tuples, so these were tuples for us before, I believe, but they've been converted into lists. But aside from that, it's pretty much one-to-one. And you can see over here, and this is the off-grid stuff. You can see I placed stuff at half pixels. That could cause problems. I think we should be fine because of the way we're converting our scroll to integers though. So you might want to be careful with that and like truncate your positions for the off-grid stuff if you're doing certain types of operations. It's just something to think about if you start running into issues with like collisions or something, or jitteriness in rendering. But in our case, I'm pretty sure it's fine. All right, so now that we've saved our map, it would be nice if we could load it. I won't create a load key binding because if you create a load key binding, then the expectation is that you can browse files and select something. I actually have that in my level editors that I actually use, but it's not super important. You could implement it with Tkinter, and that's how I do it. But I don't really want to get into that because that's not Pygame, that's something else. So you would hook that up with Pygame to do the file loading, but for our case, we'll just assume that we're loading from a certain path. So the way we'll do this is we'll go over to here and we'll say self.tilemap.load, and we'll have to fill this function in later, and we'll say map.json. So if that file exists, it'll load it. So the next thing we'll have to do is say try except file not found error pass. So we only want to load the map if it exists. And in our case, it does exist. But we need to create this load function now. So here's the other end of the nice stuff with JSON. Def load self path, and this is why I put all that effort into making sure that the data structure was easy to fit into this form, because this makes the saving and loading so much easier. We can do f equals open path, and instead of writing, we're going to read now, and then JSON.load, and you just pass in the file pointer, and then we can say our map data is equal to that, and then we just close our file. Oops. Now with our map data, we can start assigning things. We do self.tilemap equals map data, and this will come in basically as you see it right here. So it'll be like a dictionary with tilemap and everything. So we just do tilemap equals map data tilemap, and then we just go through here and we do tile size, and then we do off grid, and then that will be off grid tiles. And now if I run the tile map, or not the tile map, the editor, we see our thing is loaded back in that we saved before. But if I delete this file here and run it again, we get an empty thing to work with. So that's convenient. But you might be thinking, okay, we have this nice level editor and everything, but it's really tedious to take something like this and deal with all the different tile types you have to think about. So you have to go through here and switch your variants and do all that stuff, and then you go like this, and you just keep going like that, and you have to go through all these different tiles, and eventually you get most of what you're looking for. But it's very tedious to go through here and do this all properly. So instead of doing that, I'm going to implement something called auto tiling, where it can take all of the tiles that we have and figure out what variant each tile should become. So this is just an algorithm that we apply to all of our tiles, where it looks at all the neighbors and figures out what it should be. Another feature that I would normally add, but I don't want to get into because it doesn't really benefit you much to learn about it here, and it's a bit tedious, is to do flood filling. That's something that I have in all my level editors, but fortunately in our case we won't have to deal with too large of areas. We're mostly dealing with floating islands, as you'll see in the gameplay later. So flood filling is not super important. Auto tiling, however, is. Fun fact, my first Steam game, Super Potato Bra, I made without auto tiling. I actually did have to go through all the different variants by hand and place them where they should go. It was super tedious. Alright, so let's go over to tile map here. And that's actually something interesting to note, is that my game Super Potato Bra was, I guess, technologically inferior in many aspects to this tutorial. So what you're learning from this tutorial is past what a decently performing game on Steam had, although that was in 2018, so 5 years ago. So in here in our tile map, we'll want to create our auto tile function. So we don't have any parameters for it. We just call the function and it should auto tile everything. So let's just do def auto tile self. And we just iterate through all of our tiles. We don't want to do the off-grid stuff because, I mean, how can you figure out the neighbors for an off-grid tile? But for the stuff on the grid, you can look at the actual proper neighbors. So we do for location in self.tilemap, tile equals self.tilemap location. So that's just the location string, and then we're using that to get the value. And then we can get neighbors equals set. So what we're going to do here is we're going to look through the different neighbors. So let's do for shift in. These are different offsets we're looking at. So 1, 0, that's one tile to the right. -1, 0, that's one tile to the left. We'll do 0, -1, that's the tile above, and the tile below. So for that, we can now create a location that we're looking up. So we can do check location equals the string of the original tile's position on the x-axis plus shift. So what neighboring tile we're looking at. And then we can do plus the string of that same tile again, and we just do the y-axis plus shift. All right, should be shift 0 and shift 1. All right, with that, we now have our check location. I'm going to do if check location in self.tilemap, and then we can now do stuff here because right when this pass is reached, that means that that neighbor exists. So it's time that we go and define what exactly we want to do with auto tiling. Oh wait, we actually have neighbor offsets here, but we're using a different set of neighbors because this one is for the tile collisions where you need the diagonals as well as just the actual edge bordering ones. We don't need the diagonals for auto tiling. You could do auto tiling the diagonals and add extra cases for that, but our tile set doesn't do diagonals, so we don't have to do that. Anyways, so we want to specify which tiles we want to auto tile. So we'll say auto tile types equals, and we'll do grass and stone. Funny enough, it's the exact same thing as the physics tiles, but if you wanted to separate them, you could. All right. The other thing we need is an auto tile map. So this is going to be the rules that we use for auto tiling. So this is going to be a little bit funky. We want to say that if we have certain neighbors, then we should have a certain variant of the tile set being used. So let's say, for example, tile variant 0. If you remember, that's the top left tile in the tile set, because it was the very first one selected in the editor when you go to that group. So it's the top left one. So the top left should be placed if there's a tile to your right and a tile below. So for example, if you want that, that would be the tuples of 1, 0, and 0, 1. So that would be to your right and below you. So if these are your neighbors, then we would want to say use tile 0. So that's how this auto tiling thing works. You could add extra rules as well. So you can add, like I mentioned, the diagonals. You could add that to your offsets down here. And you can add rules over here. So it's like if you have certain diagonals, you follow these specific rules. So you can go crazy with this, but we just need some simple stuff. Now, something you have to be careful about is that the way we're going to be doing this is we'll take the list here of these two things. And because you can't use the list as a key, well, you could do a tuple. But the problem with using a tuple like this is that what if, for example, your neighbors are these two, but it comes in a different order. If you do this, then that's not a value in this map. So this order will depend on what order you go through your neighbors right here. But the hacky way to make sure that you get the order correct is to just run a sort on it so that it'll come out in the same order every time. And that way you can actually look up the neighbors properly. So what we'll do here is we'll take this as a list and then we'll run sorted on the list. So that way this list will be the same order no matter if you write it as this or if you write it like that. So it will convert multiple different arrangements down into the same key. But you can't use a list as a key, so we have to make this into a tuple. So that's a bit of a hack, but it works. So there's a few or several other rules we have to do here. So we have to do, we'll go one at a time. So I'll just paste a bunch. Actually, I won't paste them all because it's easier to do them as neighbors. All right. So we'll do this one. So that means you have a tile on your right, below, and to the left. This is tile number 1. If you want to look through our images here, you can see how these are arranged. So we have grass, and you can go top left, middle, top right, right, bottom, bottom left, left, and then middle. So that's how that goes, and we just have to go through and write down all the rules here. So I'm going to go through this really quickly. You can figure out just by looking at these numbers what they should be, but it's not super important. You won't be learning anything new, so I'm just going to do this real quick. Alright, so I wrote all these rules here, and this should be the rules for mapping out our auto tiling, and we can go back down to here and finish our auto tiling function. Alright, so if the location is in our tile map, then let's say if self.tilemap check location type is tile type. So we want to make sure that the neighboring tile is the same type as the tile itself, or rather the same group or whatever. So we don't worry about if it's a different variant, but if it's a different type, we don't want to be auto tiling with it on the border. So like if you have a piece of grass and stone next to each other, you don't want them to kind of join in on the middle. It doesn't make much sense visually. They should have a border with each other. All right, so if it meets those conditions, we can say neighbors.add, and then we'll add in shift. So that's the neighbor rule that we had. And then we can convert this neighbors equals tuple sorted, and that's the thing we were doing before, so that it comes out in the same order as that set we had before. And then now we can say if tile type in auto tile types and neighbors in auto tile map, then we have a match, and we can do the variant equals the variant for that rule, which is auto tile map, and not type, that's going to be neighbors. All right, so that's what we need for auto tiling. So now we just have to go back to editor and bind it to a key. So let's just go ahead, and I'll have to use the key T for this. Event.key is pygame.kt. So we do self.tilemap.autotile. And then if we run the editor, hopefully this works first try. We just place all these tiles right here, and then if I press T, it looks like it works. So it converted all of those mess of tiles into what we needed. So something to note is that if you, for example, do this, if you remember, we don't have a rule or even a tile in our tile set that can represent this. So you have to be careful about your shapes. If I press T here, there's no rule that meets that requirement. But if I add in a second strip there, it does exist as a rule. So you have to be careful about what types of things you're drawing with unless you actually add those extra tile types, but we don't have them. Our tile sets are just the 9 tiles that form this shape. So we can't do anything where it's like one tile sticking out like that or something. So in fact, even just a tile by itself, we can't do that either. So you have to be careful about those things. That's just something you have to do in your level editor. If you want to do a more world generation thing and then auto tile that, and you end up with stray tiles, then you'll probably want to update your tile set to support that, and then you'll change your auto tiling rules. But for our needs, this does what we need. We can create something like this, and then the grass shows up nicely. All right, so I'll make an example level here. I actually have pre-made maps, so that's what these are. You can look in here. And oh, why does VS Code show this one properly but not the others? That's funny. So this one, you can see, look at all this data. That's a map. But I'm going to demonstrate how you can do it first, and then I'll use those pre-made ones because you're not going to learn a whole lot from me just sitting here using the level editor for an hour. So let's just make a basic one just to show you. We can go create this, we'll do that. And actually we do need this now that I think about it, because there's extra stuff in that tile map that I haven't introduced yet. So we'll have to get to that later, but that's for the enemies and stuff. We'll get to that in a bit. So we can just create a basic map. We can do, oh, I don't want that. So I can like place the different types of flowers as well. And then I can go over to the stone and we can make that, and let's say that, and I can auto tile those. And then let's put in some off-grid tiles. Can put in some bushes and some trees, and then I believe where's the crate? Is that, oh, it's over here, isn't it? Yeah, here's the crate. So I'll put down some crates as well, and let's put down one more rock. So that rock will go there, and then if I save that, I can do that, and then I can go back to game. And for now, I'll actually load the map from here instead of using the maps folder that has those actual maps, because we're not ready for that yet. So let's do self.tilemap.load, and we'll just say map.json. So that'll load whatever we just exported. So if we run the game, we now actually have a nice area to run around in. And it has trees and rocks and flowers and different types of decorations. So we have these nice little boxes and these islands to run around in. A whole lot nicer than those 2 slabs of land that we had before. So the game's starting to really come together here. And While that was quite of a detour to do level editing, there's lots of useful concepts that you're able to learn from that, which is why I decided to cover that. But also, now that you have your own level editor made, you can add your own custom features that fit your needs better than a standard level editor might. But remember, feel free to use a normal level editor if you wish as well. Just bear in mind what the requirements are for how you load different files and stuff like that into a game like this. Things were made a lot easier for us because I designed the game around how the level editor would work, and then I had both of those in mind when I really did everything here. So you can make things a lot easier for yourself by using something of your own, but some of the pre-built stuff is pretty good as well.